Welcome back, those of you that are here. This morning is, as scheduled, is an exercises session. So we're here to answer your questions, help you work on exercises, most likely the Laplace exercise, since that's the one that's many of you may be focused on right now and will certainly take the majority of your time. But any exercise and any questions you may have. So I'll be hanging out here and to answer questions. I'll be largely quiet unless I'm doing so, though. And I may step off screen occasionally, but as per our usual practice, it means nothing. I'm still here to answer questions, and if you throw them up, I'll get to them promptly. Yeah, debugging the plus code is likely to involve a lot of runtime errors, as you know, your message passing doesn't quite line up, and the indices are a little off, and things are out of bound, and segfaults will show up. So, as a matter of fact, I don't think probably anybody will solve this problem without at least a few runtime issues. So don't be discouraged by that. We'll talk about the debugger later this afternoon, and it will make life a little easier, but it's not necessary for this exercise. Instead, you know, a few print statements here and there to help you see how far your code's getting so you can isolate where it's crashing will probably be pretty effective. So give that a shot. And, you know, mostly you're going to want to find, for most of you, your errors are mostly going to be when you do a bad, you know, MPI command. And you're going to want to know exactly which one of the MPI commands it is. And that's where the print statements can help. You can say, oh, I got this far on this PE to this command. And that isolates it to a line. And then on that line, you might want to print out a few of the parameters and see which ones are which. Because for many of you, it's going to be a matter of just making sure your indices are right. And you're not trying to send, you know, pointing to the wrong area of an array and trying to send it, or receiving something like that, or setting the wrong type. And those are going to be kind of inevitable to work this problem out. So your error is a segmentation fault. Segmentation faults are maybe the most common error, and it means that something tried to access illegal memory. And what that almost always means is that somewhere you pointed the compiler, your code is trying to access a bogus variable address. So for example, let's say you have our Laplace array, it's 1000 by 1000, and you point it at the end of the array and try to access another 1000 elements. You know, say you go one past the end of the row. I'm not saying this many different kinds of errors. So I'm not saying this is what's happening, but for example, let's say you pointed at the very last element in the array and you try to access the next 1000 errors or next 1000 elements to send that. That could go out of the memory pool, and that would cause a segmentation fault, a memory segmentation fault, and that's what you'd see. Now, these are a little bit, I'll say, inconsistent in that people sometimes don't get seg faults when they do illegal memory accesses. And the reason is that you end up pointing at memory of another variable that you have in memory, but it is a variable you have in memory. So we have multiple arrays. We have temperature and temperature last, for example, here. Let's say that temperature is first in memory and temperature last is last in memory. If you accidentally go past the end of temperature, it won't generate a seg fault because it'll reach into temperature last. And so it'll give you bogus data and your code's not right, but it'll run just fine. Whereas if you point at the end of temperature last and try to reach real far, it will probably go out of the memory that's allocated for the code. And that's where the hardware kicks in and says, the memory manager just says you're trying to access illegal memory, and that will cause an error. So a seg fault means you're accessing illegal memory that you don't have allocated, but you can also have memory, you can also have bogus bad addresses, accesses that don't generate seg faults because they end up accessing the wrong variable, but it's something you have in memory. So just to kind of give people an explanation for those of you new to working with compilers and languages like this. And this is true of any language that's compiled, is that this is where seg faults can show up. So you probably are pointing at something incorrectly. Another example could be if your type of your message is wrong, then instead of it being integers, maybe it's floats, and that's a bigger message and that's too big for memory. Or too big for the buffer you're receiving into. If you're receiving a message and you say you want to receive one of something, but instead 1000 of something come in, then that can go past your message buffer, and that will cause a seg fault. So seg faults are very common, but the best way to isolate them is to check the indices of the arrays, but you know, use a few print statements to home in on the line where it's happening. And then very carefully examine on that line all of the variables. Usually there'll be parameters to an MPI routine, since that's the kind of code we're doing. One by one, examine those variables. Again, a print statement will be your friend here, and make sure that your types are right, the number you're getting is right, the first element that you're looking for is the right one, and that's most likely it. And we will have a nice IDE debugger. We'll talk about this afternoon in the tools thing. We'll be using DDT, and it is the more efficient way in general to deal with errors like this. But again, we defer tools to the end because they'd be a terrible distraction for everybody playing around with the tools and getting them up and running and everything for simple exercises. And these exercises are doable without the debugger, but we will illustrate the wonderful capabilities of the debugger before we're done. Ternary operators and the MPI commands. Sure, it's regular C code. Again, this is the wonderful thing about MPI. It's a library. So like any other library, you're using the regular rules of the language. And so the C ternary operators can work for parameters, and they can be stuck in here as well. The loop indices include rows +1 and columns +1. Let's see. I think first of all, ask yourself if the bottom corner element, so the outer row of elements is the heating element, as it were, right? And the bottom corner, or any of the corners in our problem here, our metal plate problem, don't actually get used by any calculations, right? Because the metal plate itself is kind of inside that boundary. And so the element and the most diagonal element inside the boundary, so one up in the diagonal, is only accessing its neighbors to the north, east, south, and west. So that very, very most diagonal element isn't actually used in any calculation, is it? So it doesn't really matter. You could stick any value in those cornermost elements where the heating element is, and it wouldn't have any effect, would it? Possible to send one array or one vector in MPI. It's very easy to do that, and we're going to talk about that with derived data types this afternoon. So it's a very, very common thing to do is to actually send arrays, chunks of arrays, blocks of arrays, diagonals of arrays, vectors, C++ type objects, C structures. These can all be easily made into single messages and be sent. And so we will cover that in advanced MPI. But for our purposes, all we need to do is send one strip of memory. So we wouldn't find any of that particularly useful for this Laplace code exercise. But yes, it's very easy to do that in MPI. Again, addressing Enrico's question there, that suggestion is kind of what I was saying there. So if you want to think about the indices on the heating elements, realize that the diagonal absolute corners of our full data structure, which include the heating elements, right, are never actually used in the calculations, right? Because when you scan the middle, by middle, I mean everything but the outside row of the temperature or temperature last array, you're only grabbing neighbors to the north, north, up, down, left, and right. And so therefore that cornermost diagonal element doesn't come into play. So that's not when you're doing the boundary conditions or the heating element, that's not one you want to have in the calculation. So that's why it is actually that way, and that makes it correct. But probably you don't want to spend too much time. Take it for granted that the serial implementation is actually correct as you work on the parallel implementation, and that's what you want to reproduce. And then if you do that, your code will work correctly. So if you don't want to think about all the indices that are in the serial one, but if you do, that's the reason, is you want to make sure that the corners of the array, are not where that you set your heating element start and end ranges, because they're not actually relevant. We could set the bottom right corner to 1,000,000 when we initialize the problem, and it will have no effect on the run at all. You probably, so let's see, is there a reason we don't write the usual MPI startup routines at the very top of the script? You probably do want to write the usual MPI startup routine somewhere at the top of your program there. Script, pains me to see somebody refer to compiled program as script, but nevertheless, there's you should absolutely have the MPI startup routines at the top of the program somewhere. Because we need them. We need MPI init before we start using MPI routines, for example, and thing needs to know MPI rank somewhere, so make sure you put them in where you think they should go. If the code is running, but you're not getting the right answer, absolutely, it's probably the logic of the message passing is probably you're mixing up the message a little bit, not sending what you need to where or whatever. That's the tricky part of this, and so that's where you get to keep thinking about it and poking away at it. And the debugger we'll look at this afternoon would make this process even easier, but you can, in this particular case, probably figure it out without that. But that's the hard part. So it is a little bit of a battle to get everything right here. It's a non-trivial problem. And the reason that I said you're a real MPI programmer, for real, legit, when you finish this problem is because you're not going to get the logic right by accident. You're really going to have to think about it. There's no need to save questions for later. We have this whole morning is this exercise sessions for just generic questions. So please, this is a good opportunity to get into topics that you know we don't want to digress into in the middle of the lectures otherwise. So please don't hold back your questions. In this particular one here, we have this question of, is a reference discusses domain decomposition for things that aren't that local? There isn't a single reference I can cite. You know, nobody's written a book on just domain decompositions, although lots of different parallel and concurrent programming books and texts and whatever go into different domain decompositions. Instead, your best thing to do is to Google, basically, for your particular application. Google, you know, parallel implementation of whatever you're doing. So let's say it's an n-body problem. An n-body problem is a good example. By n-body problem, for those of you, I mean something like, say we're doing gravitational interaction of everything in the solar system. The planets all interacting with each other. It's not so obvious in that case how we would use ghost zones or cells or something for a decomposition. Indeed, we wouldn't. You got, you know, 9 planets, or however many planets we define these days, 8 planets, and they're all interacting with each other, and the sun and their moons and other things. And so the technique we're using here, for example, wouldn't really apply there, but you'd still want to run that in parallel. You say, how do I do an n-body problem with its, you know, n-squared interactions in parallel? And there are, I cite this as a good example because that's an important class of problems, many solutions, alternative solutions that work well to do it. And if you Google, you know, n-body problems, parallel implementation, that will quickly lead you to some great papers and great references and great techniques, and even some prepackaged code, MPI codes that people have done to deal with those problems, and libraries. And so you'll find lots of resources. It's the neat thing about MPIs, because it's so mature, it's been used for so long, that there are lots and lots and lots of solutions for huge classes of problems. So unless you're inventing entirely new, completely new ways of thinking about problems, somebody else may have helped you in your path. So Google is going to be your friend there for finding a good domain decomposition, which is equivalent to finding a good parallel programming technique. The domain decomposition, the actual algorithm itself, are so bound up together. So for n-body problems, for example, when somebody says, you know, here's a particular way of doing this problem, it's going to be the whole algorithm and the domain decomposition, everything together. And so that's what you'll that's your best path, is just Google, look for some papers and some references. And by the way, if you really feel no luck whatsoever going down that path, that's where you can talk to somebody that's got some parallel programming expertise and say, hey, you know, I'm having a hard time finding, getting a toehold into how to start here, how I might address this problem. And then somebody that does parallel programming can you know, give you some help. But I think that with MPI, you'll have at least luck no matter what you're doing, getting some initial papers and blogs and books even to talk about how to address your type of problem. Okay, that's as much as I can say generically about a particular problem. Let's see. Send and receive the temperature array of the same chunk. I didn't get a deadlock. The deadlock problem we talked about is very dependent upon the message size. Our messages are not that big. There are strips of 1,000 elements, so that's only, you know, 8,000 bytes. It's not, they're probably, there's no, you know, in all likelihood, there's no machine that's configured so that would cause a deadlock. On the other hand, as they grow larger, I have a slide later on when we talk about some ways to deal with deadlocks. On Blue Waters, which was for a long time a very, very large supercomputer, very powerful supercomputer, when we scaled this up to 10,000 by 10,000 for our hybrid challenge, it would cause a deadlock there. So our current problem is unlikely to ever cause a deadlock. If you scale it up, it could cause a deadlock, and in which case we would just use the end run around all deadlocks we're going to talk about more, which is non-blocking message passing. So we haven't talked, I just mentioned non-blocking message passing, and I've mentioned it's a solution for deadlocks, but we haven't gone into detail. We'll go into detail in the advanced MPI talk on non-blocking message passing. And you'll see that if you ever have any doubts, like, oh, is this going to cause deadlocks? That's just the answer. Just get rid of the whole issue altogether with the non-blocking message passing. So we'll look at that later, but it'd be hard to block to cause sends. Blocking message passing, remember, and deadlocks happen because the send is so big that the send can't send it in one chunk. It has to, the pipeline kind of backs up. It has to send it in multiple chunks. And if all the pipelines are backed up, that's where the deadlock comes from. Well, that's unlikely to happen with these relatively small messages. I have one more question about setting up MPI, linked to Alexander's. Is MPI init ever called before main? So MPI doesn't need to be at any particular place in your code. It just needs to be the very first MPI call. So if you have a large code, you could do lots and lots of stuff before you really get into the MPI, and it's fine if MPI init's way down in your program. However, I will say it has to be called before main. Well, in C, nothing's called before main, right? In C, main starts running your program. So there's nothing before main that's actually executing. Everything else before main are definitions and things. So it's going to be, nothing can happen before main in a C program in general. But when main starts up and starts running and calls other subroutines and everything, lots and lots of code can happen before you call MPI init, as long as you call MPI init before you do any other MPI work. So then defines, for example, defines in C code don't do anything. They're actually just, define text substitutions basically in the code. So if you can't put MPI init up there because it won't actually run. So in C code, your main program is where things start to run. So the code is not working and the temperature is still staying at 0.1 degree for that magic point. It is most likely because the message passing isn't quite working right, and that's really the entire exercise. Is the hardest part is really getting the message passing sequence correct. So keep plugging away at it there. Let's see, send and receive a head and tail array. Head and tail array. What do you mean by head and tail array exactly? Let me think about that. I'm not sure what you mean exactly by head and tail array here. Let me think if I can parse that. But there's multiple ways of doing it that are fine. But as long as things end up in the right place before you start trying to do the next computation phase, you're okay. There are lots of ways. Don't be confused just because it's running, but you're not getting the correct answer. There are lots and lots of ways to do this that aren't right. So like I said, that's the thing about this problem. I say when you're done with it, MPI, because you're not going to accidentally stumble onto the right solution. Just because it runs does not mean you're going to get the right solution. There are many, many ways to send messages out of order the wrong way. I had a slide well, I've still got these slides up here, don't I? Let me bear with me. I'm going to have a slide here. Oops. Just saying things that these are just a handful of ways you can go wrong. So, the code can run and these things, my laser pointer up. The code can run and these things could still be wrong. I mean, you could be, are you sending from temperature and receiving to temperature last, or vice versa? Is that the right thing to do? Is that the wrong thing to do? Those are things you need to think about. The boundary conditions have to be set up correctly. So there's lots of things that you can do wrong and the code will still run and give incorrect results. So don't think just because the code isn't hanging that therefore, it's just going to be correct. You really need to think about, are you implementing, basically almost all of this exercise is, are you doing, this logic? Well, let me see, better slide for the logic. Are you doing this correctly? For many of you, this is where most of the time is going to be spent. Are you doing all of this correctly? Because it's very easy to get this wrong. It's very easy to send this, this row to here instead of up to here. It's very easy to use should this be temperature or temperature last that we're looking at right here? Which array is it? So it's very easy to do this wrong and get the wrong answer. You really need to think about it. And that's when your code's still going to run, but just you're not going to get the right answer. So you really need to make sure you're doing this correctly. And that's where most of the effort in this port is getting this logic right. Slide on MPI-com null. I don't think I mentioned MPI-com null except in passing maybe here I just said, okay, here's the kind of thing you could do. So I didn't really describe it a whole lot. I'll talk about it a little bit more in the advanced MPI. I think it's useful there. First of all, the documents you should get comfortable with. So if you Google MPI-plus-X or look at one of the indices that we've got, you should be able to find some description of it. But basically, it's simply MPI allows you to send anything you want to MPI-plus-X, and it'll just be a black hole. It won't cause an error or anything like that as an address. And that can be nice to make logic if you want to make your logic flow a little easier, something like this. This way, everybody sends up, including at PE0. So PE0 is sending a message up, but since it's really going to proc null, everything's fine. So if you want to do something funny with your logic, it's just one more tool MPI gives you. You don't need it at all to make this code work. Most people, I'm guessing, aren't using MPI-proc null, but it's just one of the many little nifty things MPI does that help you if you want to write your logic in a different way. Grace mentions a good point here. I mean, tags can be a good way to make sure that your sends and your receives, because we are sending multiple messages, right? Every PE is sending messages up and down at the very least, right? So you could use tags to make sure the messages are which ones you think they are. You don't necessarily have to. You could also, without tags, make sure you send things in the correct order and enforce it that way. So you don't need tags, but they can certainly be helpful here if you want to use it to help organize where your message is going, or even verify. Even if you think your logic doesn't require tags, well, if you stick some tags in there, that can make sure, if you think that you know what your message that's coming in is, if you attach tags to it, that'll verify it. So tags can be a useful tool here. Not required, but could be. Well, when the seg fault happens, it instantly stops the code on that particular PE. Now, remember, we're running on multiple PEs, right? So seg fault's happening on one PE first, and that's usually what stops the entire code, even if you might have the same error on different PEs. So one of the PEs, although actually usually we'll tell you what PE it is too, but one of the PEs is hitting the error first. So it's on one of those PEs, it's stopping immediately. And so if you have print statements on each of the PEs, and so you do have this here, you have now inside function, whatever on PE 0, 1, 2, 3, you should, with these print statements, be able to figure out, narrow down to exactly the line, exactly the call. Most likely for this particular problem, it's going to be an MPI send or receive. Most likely, I don't want to say it for sure, but most likely an MPI send or receive is the culprit. But you should definitely, if you pick apart your print statements here, and you should be able to see it. Now, remember, as we discussed yesterday, print statements, because of buffering, can get mixed up, scrambled a little bit. So don't pay so much attention to the order of the print statements as much as say, okay, yes, I know I got here. I got here, I got here, I got here. Where didn't I get? Oh, on PE number 2, I never got to that second send. And so that gives you a clue. The second send, well, if you didn't get to the second send, then it couldn't have caused a seg fault error, but maybe you just got past, you're only getting past the second send. And that makes you think, oh, as soon as I get past, I never get past the second send. I guess that's what I'm trying to say here. I never get past the second send on PE2. So you go and look at the code and go, oh, PE2 second send, or the second send. Oh yeah, I'm sending a float instead of an integer, or whatever the case may be. So you need to put in more print statements. Yeah, exactly right. More print statements and stare at them more. And the seg fault will instantly cause the code to die right there, wherever the problem is. Okay, Dim, I think you need to elaborate a little bit more on what you're asking here, because you say you execute the Laplace my MPI.c file. So you shouldn't be executing the source. So that's a source code file. That's a .c file. So you shouldn't be executing that. You can edit that file, you can compile that file, but you shouldn't be executing that file. So you want to, like I say, either compile or edit that file. Don't execute that one. You want to execute the a.out file, probably using MPI run if you're doing this exercise. So that's probably the root of the problem. Let's see, do we need to merge all the slices to the master PE? No, you probably do not. In this case here, the manager 0 PE here is probably not doing anything particularly, particularly different than the other PEs when we're doing the sending and receiving code. So in other words, let me once again go back to presentation. So the manager PE in our code right here, occasionally does some special stuff when it's asking the user for, the input values. But for most of the time it's running, right? When we look at what we're doing with ghost zones, for example, which was there, but we'll look at this slide instead. For most of the time it's running, PE0 is no different than the other PEs, except that it doesn't send up, just like PE3 doesn't send down, but it's still doing exchanges. So PE0, it's unlikely that you want to, gather all of the strips back there or do broadcast from there or anything, at least for this exchange, this communication logic right here. For that part of the code, PE0 is playing along the same as the other PEs. How do you check for the correctness of each slice? Well, by correctness, if you mean basically how are you getting the right answer, and you might want to visualize it. So in our case, the only point when I said we want to check one quick check for correctness is to check that magic point. That was only a point on between PE3 and PE2, which was fine. But the best way to if you want to check correctness in general, you could dump all the entire array out from all the PEs to disk and visualize it. So that's that's pretty much. I think I had a little piece of code for it right here. I mean, here's how you can have each PE is going to write out to disk its section of the file in order. That's exactly what this piece of code is. I didn't step through it in detail yesterday because I said a lot of you won't want to do this for this exercise. Instead, you'll want to use this, my magic data point code. But here's a piece of code that writes out the entire array when it's done to check for correctness, and it never has to write everything back to PE0. And that's a good thing because, as I said yesterday when we talked about domain decomposition, you never want to have a code where one of the PEs, PE0 for example, has to ever have all of the data sitting in it, because that's not scalable. Memory-wise, that won't work. As we scale our code up and it runs on 1,000 PEs, do you think any one of the PEs could fit all 1,000 of the other 1,000 PEs data into it? Could they ever be merged together on PE0? The answer is no, that's not scalable. So you never want to create a situation in a scalable code where one of the PEs has to combine all of the data together. That's not scalable. That's that bad domain decomposition and a bad strategy. So here's an example where we get the full output, we get the entire output, but no one PE ever has to have it all. So if you look at this code here, what it's actually doing is each one of the PEs is getting its chance. We have a loop here with a barrier in it saying PE0 first, PE1, and it dumps all the data out. So this way, each one of the PEs gets to write out to the same file all of the data, so we end up with a file that we can visualize, has all the data. And we do it in order. We want to be careful. If we let all the PEs simultaneously write into the same file, the data could be scrambled or who knows what order. So this way we have a loop, and PE0 writes all of its data out, then PE1, then PE2. And if you put this in your code, all the data gets written out, and then you can visualize it with matplotlib or your favorite tool, or for some reason I used Excel here. You can visualize it however you'd like. That's the best way to actually check for real correctness. But I said for this particular problem, here's a little cheat. If you get this, if you get this working, you're probably good. And that's just checking one point in our entire plate. So it's not very thorough or rigorous, but I said you can assume that'll work pretty well for our problem here. Okay, well, something closing the connection does not sound, so if it's closing the connection is unrelated to your code running. Your code, when it crashes, the worst you should do with your code is it should crash and come back with one of these segfaults or some other kind of error, and you're back at the command line. So if something closed the connection, you had a problem not related to your programming, but to the way you're connected to the machine or your network or something, but that's not the programming error. Your program should never be able to close the connection. So that's something else going on there. Getting to iteration 6, and it says that the DT is equal to 0. That does sound like a programming error, and that's easy enough to happen. There's lots of ways for you to not check DT properly in this code, right? DT is being calculated on each one of the PEs. They all have different values for it, so you need to figure out which one you really want to pay attention to when it's time to quit. So a little bit of logic to make sure DT works right is important in this code, but it shouldn't be able to close your connection regardless. Oh, you closed the event because it was hanging? Yeah, well, as said there, Control C is your friend there. So it didn't close the connection, it just hung. So if you Control C when your code is hung, give it a second or two at most, and it'll come back to the command line. Well, I can't help you on your digging through and looking through your code for spoilers, because or doing it for you, because that would be spoiling it. I mean, if you want it to, there's a solution sitting there you can look at. So I don't want to do that, but I will say that this is a good chance to exercise the standard debugging practice of, if you know what you wanted. So first of all, as I told everybody, do what you want to do on paper first. Sit down, make sure you've got your ghost zone exchange worked out, so you know exactly what you want to do. Then you can use print statements and have it go through your code, say, am I doing exactly what I think I'm doing? And if you do that, so for example, if you say you're getting zeros everywhere, well, if you're passing around messages that don't have zeros in it, print the message out. Is it 0? If it is, then go, okay, well, why am I sending zeros? And you go to your send and see what you're sticking in your send. So you should systematically be able to figure out why you're getting all zeros just with print statements. Now, again, we're going to look at a debugger in a little bit, and that makes it even faster and easier to home in on directly what's happening in your code. But if your code's running right now and giving all zeros, that gives you a very good place to start to debug it. You use some print statements to start to say, why am I sending zeros? Why am I not sending some values that have, have some heat in them, so to speak? And print, with print statements alone, you should absolutely be able to home in on things. Now, you have to be systematic. You can't just randomly grasp at straws because, well, you can, and a lot of people do that, and I'm tempted to myself at times, but that doesn't necessarily home in on what's going wrong. Instead, make sure you got some print statements, you're printing out what you're sending, printing out what you're receiving, and say, oh, I am really sending and receiving what I think I am, and I think this should be non-zero, what I'm sending, and oh, well, look, I'm sending zeros. Why is that? Oh, look, I'm sending from temperature, I'm receiving the temperature last when I thought I was doing the opposite, or something like that. So it is up to you to home in on that problem here, but you do have the tools to do it. The OpenMP timing is much better than MPI here. So that's not surprising at all. We're going to do some comparisons we'll look at briefly some comparisons between OpenMP and MPI when we're done, but I can take this opportunity here since we have some time to discuss it. And that is that OpenMP, so we actually went into yesterday's Q&A session at the end. I went into this in a lot of depth, but I didn't assume everybody stuck around for it. And I'll talk about it again later on today briefly. So I don't want to beat it to death, but I'll go over it again. OpenMP, since it's meant to work on just a local node and all the cores, you might think is absolutely going to run best when we're running on a small job like this with only 4 PEs that are 4 cores. And MPI should be slower because it's got some overhead of having to send messages and whatnot. And that's actually not the case all the time. Sometimes the MPI is even faster than the OpenMP, even on a single node. And that could be because the MPI version, when you do the domain decomposition, breaks the data structures up in ways that make it work really well with the cache. So we're not going to go into those details, but it's the reason why sometimes MPI works better even on a single node, where you might think OpenMP is the right tool for the job. But the differences are only a couple % here and there. And indeed, that's the case you should find right here is the OpenMP on 4 cores and the MPI on 4 cores are roughly the same. The main reason you'd ever do the MPI version, though, isn't to run on 4 cores. It's so that eventually your code can run on 4,000 cores. As you're finding out right now, the MPI port's a lot harder, right? It takes more effort. So the reason you're doing it is so that things can scale up. So if we were only going to run this on 4 cores and only wanted to speed this code up 4 times or 8 times or something, I would never suggest somebody get involved with MPI here. It's just too much work to port a code to MPI if you want to speed something up 8 times and it's already a serial code. Just go, OpenMP will probably get you there with a lot less effort. But once we've got an MPI code and we can compare them head to head, even on a single node, they should be roughly comparable. Again, sometimes the MPI is even faster because of the way it breaks things up. But our problem right now, Laplace problem, is very small. Our data structure is only 8 megabytes. That's so tiny, it actually fits into the cache. The whole thing fits into level 1 cache on this machine. So that alone tells us this is a very artificially small problem, not very challenging. And the fact that it fits into cache entirely means it's going to have some relatively distorted results compared to when we scale things up. Now, I have some other slides. I've already pointed to a few of them where I say we do scale this up to 10,000 by 10,000. It starts to be a little bit more interesting. Now we've got a problem that's gigabyte size, and the results start to look a little bit more typical where MPI takes the edge when you spread it out and et cetera. So we've thrown up a few of those graphs so far. And still 10,000 by 10,000, by the way, is very small still. When we do the Laplace exercise review, I'll suggest that for those of you that are interested in this problem to pursue it, go to a 3D version of this. What if we do 10,000 by 10,000 by, well, 10,000? Now we got a serious problem. We got a very serious problem there, supercomputing level problem, in which case MPI is going to be the only way you can fit it onto any machine. So these, as a matter of fact, that one will be enormous. So these numbers right now, when the problem's so small, don't read too much into them, but they're not terribly distorted either. Okay. Don't feel bad, by the way. Struggling harder, Grace, is probably true. You got to struggle harder, but don't feel bad. This is a difficult problem to do in the hour or two that we've invested so far. That's why I said most people, you know, when we used to have a hard time limit, and then I'd go over a solution, which I look back on now and I regret that because it cut off a lot of people. We only had 3 hours, and some people were fine with, you know, 3 hours. Well, nobody used much less than 3 hours, but people that were really comfortable with the material and been doing a lot of programming recently could do this in 3 hours. So, you know, we're not that far into it. So don't feel bad that you're still, you know, struggling with it, as you say. Lots of other people are too. I'm sure probably most people are still working on this problem. So it does take some time and effort. This is a lot harder than our earlier exercises, without question, because it's MPI. But continue, and because when you're done and you've beaten this, you've succeeded in your struggle, you're an MPI programmer, because you can't do this without actually putting in some real effort and understanding. So I'm speaking not just to you, by the way, I'm speaking to everybody out there, because most of you right now are still plugging away on this. Okay, everybody, as per the agenda, I said we're going to do kind of a review of the Laplace exercise without it being a spoiler, because many of you, maybe most of you, are still working away on the Laplace exercise, which is expected and it's good. And I can't encourage you enough to complete the exercise, so I'm not going to ruin that for you right here. But we'll kind of take a look at some issues that you may be working on right now, or may have encountered if you did solve the problem. And so this will be kind of like a mid-development review here. First of all, let me get this thing working. Okay. First of all, like I said, I'm not assuming here that you're finished at all when we're doing this. If you want to cheat and look at the spoiler, look at a solution, it's already sitting out there. So you shouldn't feel deprived of that. If you really want to see here, what's a working solution here, you've got one, at least my version of it, sitting out there already. And there are multiple ways you can implement this. But I think mine is a pretty basic, straightforward one that's sitting out there in your solutions directory. Let's see, question, is there a cheat sheet for MPI? Unlike OpenMP and OpenACC, where there are some great cheat sheets that I recommend, that I use myself occasionally, that sum up all the directives. So if you go on to openmp.org or openacc.org, you'll notice that they have a nice cheat sheet there you can print out. It's a nice little handy reference. With MPI, I don't know of a single cheat sheet. And that's maybe because, as you're about to see in the advanced talk, there are a lot of routines that you'll want to use as you get more experienced. So it's a little harder to sum up on a single cheat sheet. You might think because we're only using a dozen or so routines so far, that would be a good cheat sheet. But I'm going to show you, I will show you in the advanced talk here very shortly that there are a lot of related routines similar to what we've been using that are trivial for you to use, and will make life a little bit easier for you because they're grouped in these kind of families. So you already know how to use them. You just don't know that they exist yet. We'll show you that they exist in the advanced talk. But they add up to being a lot of routines. So it's kind of hard, I guess, to make a cheat sheet, or it's harder. At least there isn't one sitting around in front of that MPI.org or MPI forum or whatever. There's no MPI.org, the MPI forum or anything like that. Okay, let's. Somebody has an MPI cheat sheet. So as soon as I say that, as a matter of fact, I've got to take a look at that and see what it is. Let's see how somebody has decided to summarize MPI. It is a rather sparse cheat sheet. So yes, so it would work for our first couple of exercises, but won't get you much further than that. So that there is somebody attempted a cheat sheet. It's probably for a seminar or workshop like this that somebody did, because it's certainly far from being usefully comprehensive. So I cannot recommend this cheat sheet too much. It's deceptively missing many useful things. But I'll leave that up to your judgment. Certainly take a look after we do the advanced talk this afternoon. I'm going to describe an awful lot of very useful things that are not on this cheat sheet, tons of them. So you can use your own judgment, but somebody has certainly called something a cheat sheet here. Okay, so let's take a look at, and let's see, there's another cheat sheet maybe out there. Well, I'll take a look at some of these after, but again, maybe after the advanced talk today, this afternoon, you'll be better positioned to see what you think belongs on a cheat sheet or not, because as I said, MPI's got a lot of really useful capabilities that I don't think can really be fit on a single page. At any rate, we are going to take a look at a couple of things that you might be either have done or be involved in right now, which is with the Laplace code, which is, first of all, decomposing the data structure. As I said, we kind of really told you which way to go with this. And after we do the advanced talk this afternoon, you'll see it's not hard to do some alternatives like our original 4 squares instead of 4 strips thing. It's very easy to do alternatives, but this domain decomposition that I've kind of strongly suggested that you start with should be working out pretty well for you in terms of, at least it shouldn't be confusing to you what you want to accomplish. The ghost zones technique that you need to implement, I hope you can sit down again with a piece of paper and a pencil and know exactly what you want to exchange between the PEs. Now, implementing is where the work is, but I hope that you've worked out what you want to do first, because that's important. If you just start typing into the code, if you just grab the serial code and start typing MPI sends and receives in, you might shortchange the amount of effort you want to put into making sure you get all the indices right. And making sure, am I sending from temperature or sending from temperature last? Am I receiving into temperature or am I receiving into temperature last? Those kind of things, I hope you work out before you just start typing. This is not one of those kind of problems where you can just start typing the code and eventually it works. Another thing that I think you've all discovered by now, although I certainly explicitly mentioned it yesterday, was that unlike our earlier approaches with OpenMP and OpenACC, we've got to go everywhere in the code that our decomposed data structures live. So everywhere in the code where you've got temperature and temperature last, you've got to go in and tweak those things. Now, it's not a lot of effort. Most of the effort in this port, I think you're finding, is in the sends and receives, the communication part of our code, right after the computation part. And that, again, is typical of MPI ports. That's where you spend most of your time, is implementing that. But you still have to go everywhere in the code where the variables that you've decomposed live and make sure that the logic for there lines up. And that includes the initialization routines and the print routine as well. On the other hand, I think you are hopefully maybe pleasantly surprised by the fact that the science of the code, the actual part of the code that does that Jacobi iteration, you might not have had to touch that at all. And that is also typical of MPI ports. It's nice in that the actual guts where the science is implemented, you don't have to rethink all of that for most of these kind of MPI ports. Deadlocks or something. We had some questions about deadlocks this morning. And nobody should be seeing on bridges with these size messages deadlocks. Now I qualify that. I say bridges with these size messages because where a deadlock shows up, where the messages get so large that the sends start to block, is a fuzzy line. It depends on the implementation, the machine you're on, some variables that you can actually change in the environment. So there's a lot of factors. So a well-written code doesn't allow deadlocks to happen under any circumstances. But so far, none of you should be running into deadlocks. But let's see how that could happen, because it has happened with these exercises in the past and workshops, depending on other platforms that we've used. So here's our ghost zone exchange. Looks something like this, right? This is what we're trying to do with our ghost zone. And if we implement this by just saying, okay, everybody do your send to your left and send to the right, and then receive from the left and receive from the right, this is where a deadlock could happen. Whereas this slightly different variation here, send to the left, receive from the right, deadlock won't happen here. So let's see, can we understand why that is? And by the way, this did happen to us. We were using a machine called Blue Waters for a while for this workshop. Very big, powerful, capable machine. But when we scaled it up to do this 10,000 by 10,000 size version of the Laplace code, same thing you're doing right now, except the bigger plate, it would hang. So even though those messages were only 80,000 characters, 80,000 bytes, it's not that huge of a message, but it was enough to hang Blue Waters, which is a powerful machine. So, this one wouldn't work and this one would. Let's look at exactly why that is, because it's not hard to see. So Here's what happens in the version where we send to the left and we send to the right. So everybody sends to the left. Okay, that's fine. PE4 is a neighbor to the left, so it doesn't send to the left. Everybody sends to the left, and then everybody goes to send to the right. And so this is what's happening after these first two lines are executed. And this is where the deadlock pops up if the messages are too big. Because if the message is big, PE3 is waiting for PE2 to receive the message. Likewise, PE2 is waiting for PE1 to receive the message. PE1 is waiting for PE0 to receive the message. And PE0 is waiting for PE1 to receive its send. And so this is a deadlock. And this would actually happen to us on Blue Waters. Now, here is where if we do send, receive, this pattern instead, the deadlock wouldn't happen. Okay, they all send to the left. And only thing is PE0 doesn't have a neighbor to the left, so it's not doing anything just yet. It doesn't have anywhere to send. So now when they go to receive, PE0 can receive that message. Okay, now finally, PE1 is unblocked from its send, and it can receive its message, and PE1 can send. Okay, now PE2 is not blocked anymore, so PE3's message can be received, and it can send. So we kind of have this uncascading unblocking. It's not super efficient, but at least it doesn't hang. So this is why this worked and the other one didn't. Now, I don't want to have to worry about this stuff. I don't want to have to think this stuff through. And this is why as soon as my messages get large, so anything I'm sending that's not tiny, instant, little small int or float, anytime I'm sending arrays, I just use the non-blocking sends and receives that we're going to see this afternoon. Now, we didn't start off with non-blocking sends and receives because they're a little bit trickier. They require a little bit thought, and we didn't need them to make our exercises more difficult than they already are. The Laplace exercise is already, it's a serious exercise. You're biting off a lot. So it'll work fine with the messages that we're sending of 1,000 by 1,000. But as things grow and you scale it up, if you do a larger version of Laplace code or a 3D version of Laplace code, you could run into this. But we'll see the solution to make sure we don't have to think, oh, could this happen? Could that happen? We're just going to get right by it. Okay, if you run this to convergence, you get some timings here. Our serial code, we know we're starting with, takes roughly 20 seconds. And we're going to find as we run this thing on 4 cores, we get roughly a quarter of that at the time. So we're speeding up pretty linearly. And that in general, by the way, is the theme of MPI codes. MPI codes, you can hope scale linearly up to thousands of nodes. And in our outro talk, we'll talk about, is that reasonable? Should I really expect to scale to thousands of nodes? Somebody told me about something called Amdahl's law that should factor in there. We're going to talk about those things in the outro talk. But at the moment, we do have the nice simple case that we do seem to be speeding things up by about 4 times. Now, a few of you yesterday took the experiment and ran on multiple nodes. So instead of just running on 4 cores on a single node like we're doing right now by default, when you type interact-n lowercase n4, instead, a few people yesterday took some initiative on their own and decided to run across nodes. They were asking the question, when I run across nodes, it's a tiny bit slower. Well, it's kind of what you'd expect because now we're spreading the cores out so that I need to communicate over the network instead of they're not communicating within the node, probably using shared memory. So now they're communicating over the network on different nodes. And so there's a little more latency and it's a little bit slower. And so, but still roughly 4 times. And so that's good. We expect nice linear speedups. And this is how you could run this on 4 nodes. And again, I don't suggest people start doing a bunch of multi-node experiments and everything right now because it's hogging a lot of nodes and we're all working away at once. It would be a problem, although at the moment we're fine. But you can do those experiments later if you want to. And again, you'll find that our network on bridges is pretty fast. So it doesn't slow down much, but a tiny bit as we go over more nodes. Now this is what, when I visualize this thing, this is what my final answer looks like when I visualize it with the debugger that we're going to talk about this afternoon. So we visualized the results yesterday. I had a little Excel graph up there. I've had somewhere else in this, some matplotlib stuff. Here's my DDT visualization. So DDT is our debugger that we'll talk about this afternoon. Inside the debugger, it has a ability to do parallel visualization. It's smart enough because it's a special type of debugger. It's a parallel debugger. It can actually glue together the 4 strips of our problem back into one visualization automatically for us. It's nice enough to do that. And here's the answer when it does finally converge. And it's what we kind of expect. Very cold in this corner, very hot here. This is neat in DDT. You can move it around interactively and zoom in and zoom out. So I just took a snapshot of it, but inside of the debugger itself, it's very interactive. And so here's our solution when it's finally converged, and it is what we expect to look like. Very hot down here and drops off pretty quickly. That might catch you off guard. It drops off rapidly, so the plate gets very cold quickly, but does pretty much what we expect. Let's see here. We have a few questions I see jumping in here. If we use tags here, would it still block with 2 consecutive sends? Yes, because it might block, the first send is the one that's going to block. So tags, it's an interesting question. You know, tags mean we can start grabbing messages out of order, send receives out of order. But if the first send is going to block, then it won't even get to the second send with a different tag maybe. So tags wouldn't be the solution of blocking here. I can imagine cases though where tags might affect the way things pile up and block. But as I said, the second I'm even concerned that a certain type of data is so huge that it could block, we just move on to non-blocking. So, but it's an interesting question. Tags in some circumstances could kind of change the order and unblock things. Probably wouldn't here for the way we're doing things. 4 nodes versus 4 cores, shouldn't we see a bigger gain? Well, if I decided to use the nodes, all of the nodes, yes. So in this case, I'm spreading out over 4 nodes, but I'm only using 1 node, 1 core per node. So to be fair in this comparison, or to make this kind of comparison, I'm only using 1 core per node. So when we spread out over 4 nodes, we're only using 1 core on each node. Now in reality, if I'm a sane person, if I spread over 4 nodes, I'm using all the cores in all 4 nodes. But we're not doing that kind of test here. In reality, if I'm smart, I'd use all the cores in our nodes to begin with. So I'm using 128 cores on each node, and then on 4 nodes. So I'm using 512 cores if I'm using 4 nodes on bridges, ideally. So we're not doing that kind of test here. Instead, we're spreading out our single 4 PEs from being on 1 node to being on 4 nodes. That's why it's roughly the same amount of time. But normally, if I spread out into 4 nodes, it's because I want more computing power. And yes, I'd take advantage of more cores on more nodes. But that's not this particular test. Is the rapid drop-off a function of incomplete convergence on this temperature thing here? It's a fair question, even though it is, yeah, it's more about the simulation. Now, the rapid drop-off here, I mean, this is complete convergence. The solution here is converged pretty much to the proper mathematical answer. It's just because there's a lot more cold out here than there is heat, you know, really. I mean, remember our heating elements drop off. There's 0 on really 3 of the corners here. So this is the correct solution. Our solver is pretty accurate, and it's run to close enough to convergence that this is the correct solution. If we did this perfectly, or even, you know, tried to solve it analytically, we'd find out this is what the solution looks like. It really does fall off pretty steeply here. Can I repeat why scaling off node is typically better? Well, so scaling off node costs us a little bit in terms of we have a network involved now, and we have to transfer things across between the nodes over the network. So it's going to cost you in terms of we're introducing some latency into our code at the very least, and possibly some bandwidth bottlenecks. So when we scale off nodes, it's not better in the sense that you know, the communication problems are better or anything else. No, it's just that we now have more computing power. So 1 node on bridges, for example, has 128 cores. If we have 4 nodes on bridges, we've now got 512 cores. So scaling off node, when I say it's generally better, it's because we're just recruiting more computing power. We're going with a bigger, more powerful machine. So that's the reason why scaling off node, scaling off node is just scaling up in that sense. And scaling up with MPI means you run faster. You've got more computing power. But scaling off node doesn't buy us intrinsically inherently any benefits, because we've now got a network involved, and that's always going to, you know, potentially be a bottleneck. Let's see. 4 nodes together with 4 codes. We do 4 nodes with 4 codes. I'm not sure exactly what that means. You might want to say that again. 4 nodes with 4 codes. Would we do decomposition, say, with 16 chunks now? So with 4 nodes, I'm sorry, that's just 4 nodes with 4 cores. That's what you mean. Sorry, my own in-head autocorrect doesn't work so well. With 4 nodes with 4 cores, we do decomposition with 16 chunks now. That would be, you'd want to, if you did. So if we had 4 nodes and 4 cores on each node, so we have 16 PEs. So if we have 16 PEs, we better have at least 16 slices, or else what are the other PEs going to do? So yes, if we went to 16 PEs, then we want to have 16 slices at least. So yes. And that's why it's nice to make a data decomposition that's flexible, that your code starts up, says, how many PEs am I on? This is how I want to dice the problem up, because that allows the user to say how much machine can they grab at a point in time, and your code will just run correctly. Is the figure a plot of the temperature of the bottom row over time? No, not at all. This is a steady state problem. So when we're done, when our solution's done, it's saying this is what it looks like at the end of an infinite amount of time. This is what it should look like with no time element involved. So this is just the temperature of the metal plate. There's hot, low is cold, and here's our two-dimensional plate down below. So it's just, there's no time element in this particular graph. Getting to know MPI feels like you cannot escape multiple if-else conditions. You concur with experience. There'll always be corner cases. Well, I mean, it's true that a lot of times with MPI, there's some logic required. Say, if I'm PE0, I don't send messages left or right. But we'll see with advanced MPI stuff, we can set things up to minimize that a whole lot. So I don't want to comment too much on that until you see the advanced MPI, which greatly simplifies the logic for domain decompositions. Brings a lot of tools into play to make, as you can imagine, when I talk about a real problem and, isn't the square metal plate, it's a weird turbine blade, right? It's some oddly shaped thing. You can imagine the domain decompositions get really tricky. Well, fortunately for us, MPI brings a lot more powerful tools to bear to keep track of those domain decompositions, and it can eliminate a lot of the bookkeeping and the if-else logic. So an awful lot of the bookkeeping MPI will do for you. So, but I'll prove that to you this afternoon. So for now, just have to take my word that no, MPI doesn't necessarily have lots of bookkeeping involved for the the corner cases and whatnot. Not some, but we'll see how we can minimize it with some new tools. Let's see. Temperature will drop off. Same speed regardless of the cutoff. Rate of drop is purely a function of boundary temperature. Yes, that is true. Interact dash capital N4 dash lowercase n4 means it means 4 nodes and just 4 PEs. So that's, and this is because I don't want to get into platform specific stuff because you're not here to learn about bridges, but this is a local thing we developed in-house for bridges to avoid using the queuing system. So interact is our own local command, and it's pretty friendly. You can type interact-help and see how it works. But I don't want to spend a lot of time teaching you just about bridges. But this is so people don't have to use our Slurm batch system all the time. You got a little peek at it on Tuesday with the GPU jobs. But to avoid using Slurm all the time, we developed this interact command. And the way our interact command, capital N is the number of nodes, lowercase n is the number of tasks that you're running PEs. So this is going to be 1 PE for each one of the nodes. Pretty wasteful, by the way. You typically wouldn't want to run like that, but that's exactly what this means. And by the way, we set up interact to look kind of like MPI run because we know people are familiar with MPI run. And MPI run typically looks like this too. Capital N will be the number of nodes, lowercase n will be the number of PEs you're using. And this is just as which part that we want to use regular memory nodes. That's what this is in here for. Okay. Let's see. So that's how the code scales up. Oh, by the way, I think it's important to point out too, is that, to keep life simple, we haven't talked about using any of the regular serial optimization flags on the code either. We haven't done that. And that's silly. I mean, in the real world, anytime you write a code, you want to do one of the easiest things to do, which is try some different optimization flags the compilers have. And usually you want to spend, you want to give yourself a part of an afternoon to play around with all of those because some of them can be really effective and really speed your code up. But the baseline that a lot of people just start with is the -03 optimization flag. So this is a flag pretty much every normal compiler has. Compiler flags are, of course, compiler specific, but almost every compiler has -0 flags for optimization level. And 03 is almost universally a way of saying, give me your most aggressive normal optimization. And so that's what you normally do when you're done writing your code and you think it's running, you compile it with -03 at least. That, although lots of other flags can be helpful to you here, it's a topic we won't go into, but -03, right away we could see it takes our serial code and speeds it up a lot. So you just do that, just make your serial code more efficient. It's one of the nice things about working with compilers. Compiled languages have lots of abilities for the compiler to ferret out all kinds of optimizations. And so we can see in the real world, after I get my code debugged and working, then I compile it with better optimizations, and then everything speeds up a whole lot. And then our speed up actually with MPI is even a factor of 5 because it's super scale, it's super linear there, you'd say it, because things get even smaller and fit into cache even better. And so it's an artifact of being such a tiny problem. But we in all of our exercises, including the OpenMP and the OpenACC ones, we've ignored just regular serial optimization because it would just be one more confusing factor in the mix. But of course, with your real code, you want to start using compiler optimization flags just to make your serial performance better. Okay, and this is something that we've come back to. Matter of fact, people have asked the question almost every question session and multiple times in between. So I've had this discussion now 3 or 4 times, and that's that our OpenMP code is it really faster than our MPI code, even on a single node? And since most of you were probably here for one of those multiple discussions of it, I'll simply summarize it and say it's because when you write an MPI code, all that extra effort you put into doing your domain decomposition usually buys you better, for reasons we won't go into, makes things work better with the cache. And so an MPI code, even on a single node, can often run better, not a lot better, but a little bit better than an OpenMP code. And you think OpenMP is the tool just for running codes on single nodes? It should be best at that? Well, MPI can be even a little bit better there, even on a single node. But the MPI effort is so much greater that if you were happy running on a single node, you'd probably be just use OpenMP, use a few directives and call it a day. You wouldn't want to do a whole MPI port, all that extra effort just to buy a few percent possibly of performance. Not even guaranteed. Okay, let's see. What is the advantage of MPI in comparison with OpenACC? Well, they are very different things. So MPI doesn't allow us to use GPUs. OpenACC allows us to use GPUs. So they are very, very different roles. They are orthogonal to each other. And we'll find out this afternoon in our hybrid talk that we often can use them together. If you've got a machine with GPUs and you want to use multiple nodes, then MPI and OpenACC are the tools used together to access the GPU computing capability and the internode communication of MPI. So MPI and OpenACC work together to let you use more than one node's worth of GPUs on a machine. And these days, that's any supercomputer like Bridges. If you run on a GPU, you might want to run on multiple nodes of GPUs. And as I showed you when I talked about the top 500 list, and we showed you the top 10 machines there, they all have accelerators, and you want to use both the GPU and multiple nodes. So you need MPI and OpenACC. So this is something I won't get into too much here because we're going to do it this afternoon, but even with the simple Laplace code, there are some easier ways to do things with the advanced MPI routines. And I didn't want to overwhelm you and confuse you with too many options. So we use the basic tools here, but we'll find out that there are even more convenient, but more flexible. So it takes a little bit more thought tools available to us in MPI. And we'll get into all of that with the MPI Advanced talk. The MPI Advanced talk, I think, it's a fun talk once you're an MPI user, because you start to go, oh my God, there's all these great tools out there. MPI will do so much of the heavy lifting for me as my code gets more complex. So I hope you'll find it interesting, but we'll save these topics for that talk, which is coming up after our break. And here's an example right here of using some of those fancy tools. So I'll save it for the talk later today to do, to bundle everything up in one. So yes, this is redundant with what we'll do this afternoon. I won't waste any time on that. Now for the Laplace code improvements we can do with the stuff we'll learn this afternoon, there's tons of stuff. Like I said, I'll defer till later on that. On the other hand, we can make our problem a little bit more realistic quite easily. We could go to 3D. I hope you can all see how easy it would be to turn even our serial code to 3D, right? We just add an extra dimension in, right? So now instead of rows and columns, we go with rows and columns and planes. Instead of I and J, we got I, J, K. It's not hard to port this code to 3D and start to look a little bit more like a real simulation. At which point, when we go to 3D, our messages we want to pass are going to be surfaces between two different blocks of our 3D code. How do we pass surfaces of data? Well, we'll find out this afternoon how we can do that with user-defined data types and non-blocking messages. We'd also find in the real world that our shape of our object we're interested in, once again, isn't going to be a square plate or a cube if it was 3D. It's going to be some object with some structure to it. And the most common way to deal with objects with weird shapes to them is to break it up into a mesh. So here's an example from an MPI code I worked on for doing earthquake simulations. And earthquake simulations, you're trying to predict the way that a fault's energy will be released through the ground in waves. And those waves travel through different geology. And the geology will bend and reflect and refract the waves in ways that make it very different on the surface, where some energy, on the surface of an earthquake, one area can get a tremendous amount of damage, and if 2 blocks away, you might have nothing shaken at all because of this wave behavior of earthquakes. So this simulation did that, and it was important to capture that behavior, that the geology of the ground, which is very irregular, got captured. The ground has underneath the earth, around a lot of earthquake zones, there's hard rock, there's soft soil, there are things in between. So when you turn that into a mesh, it's a very irregular mesh. Even though the area we were doing was a cube in the ground or a slab in the ground, the mesh is very irregular. And so you end up with a typical finite element irregular mesh. And you say, okay, how do we break this up? If we break this up into regular cubes, just in the ground, that would be easy to do. but some of the cubes are going to have a lot more elements than other cubes. And that would be a poor load balancing. Some of them would have way more work than others, and they're going to take forever to do their job. Other cubes would get finished much sooner. So instead, after you do this mesh, and here's, again, this is a distant picture of this mesh. But if we zoom in on it, it's a tetrahedral mesh. After you do this mesh, you want to break up all the elements with roughly this number of elements in each PE. Well, there's no way to do that. It's not going to result in some weird shaped lumps. And that's what this picture is right here. Each one of these colors is a different PE. So this dark green right here is one PE on the corner. And its shape is a pretty weird lump. Even weirder shape here is this light green next to it, or this bluish aquamarine color right here. You can see the shapes of our PEs are very weird because we want to have some good load balancing. And we're dealing with irregular shapes to begin with. So now the messages that we need to pass between these PEs are some very irregular surfaces. There's still a surface. We're still using this halo technique, these ghost zones on the edges, but you can see that the surfaces have very, very odd shapes to them. MPI deals with this just fine. We'll see that with this afternoon's technique. So this is, as we evolve the Laplace code to make it more realistic, MPI will give us the tools to work with that. Okay, let's see. I saw a few questions pop in there before we take our official break. Let's see. Is this earthquake simulation open source by any chance? The engine of it is indeed. It is, the engine of this is called Hercules. So if you Google earthquake simulation Hercules, you will find the pointers to this engine and its source code, which is still maintained by a few friends of mine. Actually, I misspoke. I don't know if it's open source. It's their project, which they have worked with lots of people on. So they control it. They are at liberty. I don't want to speak for the maintainers, so I don't know that it's open source, but they are open about it. It's probably my best way to put it. So Google it. You'll find the repo for it, and you'll find the current maintainers of it. But it is a good example of a sophisticated code that does load balancing, generates the mesh in parallel itself. The mesh generation to do this is also parallel because this is meant for huge problems with many billions of elements. So even creating the mesh is a parallel problem. So it's a very, very powerful engine behind it. Okay. MPI can be more flexible and using large number of hypertext. So that's it. Standard way to decide on the data load balance decomposition. No, it's very problem dependent, but there are a number of engines out there, like Hercules is one of them, and even more dedicated focus tools like you'll find in PETC library. So PETC is an MPI-based solver. It will do meshing for you. So there are meshers out there. There are a number of different meshers out there, paramesh, that will do meshing and decompose. So meshing is part of the decomposition, right? When you get into tricky problems like this, generating the mesh and doing the decomposition of the mesh are very entangled problems. So there are parallel meshers out there that do the decomposition for you, but they're kind of packages that you can use and build your own MPI code around. So there are a number of those out there. Parameters. Anyway, there are a number of them that are very good, but there's no standard way because there are different considerations to different things. If you're using an explicit method, then you need more than the nearest point in your neighbor. Anyway, there are different considerations that mean there are different reasons for going different types approaches to decomposition. But because the general principle is pretty universal, there are some packages written and algorithms discussing how those packages work to do this. So it's not standard, but there are a handful of very generally useful ways of doing it. Are these shapes non-rectangular because of non-rectangular meshing? Yeah, basically, the root of it is that the Earth, the geological structures in the Earth underneath this in the ground, the lumps that are making up the geology are non-rectangular to begin with. So the Earth, the geology is very non-rectangular. So then when you go and you mesh it, that becomes very non-rectangular. And then, then when it's time to break it up, it's non-rectangular. But underneath it, the physical driver for this being non-Cartesian is that the geology is very non-Cartesian. Okay, thank you for the link there to Hercules. It's more common to use C than C++ with OpenMP or MPI for that matter. I'd say these days C++ is probably the most popular way to build these projects, and C++ because kind of almost a superset of C, gives you, lots of ability to throttle it back and pick and choose, how much you want to use of that C++ framework. So C++ buys you, a lot of newer, nicer things to organize your code, but you have to be careful not to use the pieces that make it hard to get good performance or keep things, optimal. Like I've mentioned several times already, like using the standard template library can get you into trouble if you think that, that a multidimensional vector is the same as a multidimensional array. That's like a quick way to get in trouble with scientific codes. So most people these days, if I had to pick something, most people are using C++, but the experienced people are careful about which pieces of C++ they use. And by the way, it's not just true of HPC, that's true of almost every C++ project, right? If you look at Google has a guide to C++, which is basically, here's the pieces we forbid you from using of C++. They do an awful lot of C++ work, right? Video game companies, some of them are even posted online. I have a student in my class this spring who went off to work for, I want to think which one of the video game companies is. It's one of the ones that they do, one of the major video game engines he went to work for. And it's not Unreal, it's another one, but they publish online, they make it publicly available. Here's their C++, here's their programming guide, they call it. And it's a bunch of things you're not allowed to use in C++. Like, for example, nobody allows you to use polymorphism at all anywhere that's got C++ projects, because it's just a bad idea in general. But they, everybody's got C++ guides that pair back C++. So you'll find in HPC, a lot of projects use C++ as their programming language, but then they have limitations on which features from C++ you are allowed to incorporate in your code. Yeah, all the big game, it's not, was it Unity? I don't know, come back to me in a second here. But yeah, all the game engines are C++, every game engine C++. So, but those game engines, nobody's allowed to go to work for those companies. They just say, use anything out of the C++ standard that you want, not even C++ 11, let alone, C++ 20, which is, it rolls in even more. Instead, it's always a hugely pared back version of that. And in HPC, that's equally true. You don't just want to use anything in a standard. It will get you into trouble. In organizational ways is what a lot of people are concerned with, but in HPC will get you into trouble in performance ways very quickly. But most projects these days in HPC that are C++. Isn't HPC still heavily Fortran based? There is a ton of Fortran in HPC as well. And that is because Fortran is the only language up until Julia basically came along that does multidimensional arrays properly. So, and that sounds like an editorialized comment, but I will defend it strongly. So, C++ multidimensional arrays are not fun. As a matter of fact, one of the first things you do is figure out how are we going to deal with multidimensional arrays in C in a nice way. Fortran is the only language that has great multidimensional arrays that's really shaping and slicing and everything. And it also is the only language that consistently over the years said performance is the objective here. So we're not going to allow any nifty feature in our language that's going to kill performance. So that's why typically the fastest versions of codes are the Fortran one. And so we talked briefly about that with our restricted keyword in C, like the Fortran by default, everything is that restricted kind of approach. So Fortran is still very heavily used where performance and maintainability of mathematical codes is important because it's still got all the features you want. Julia may or may not intrude into that space. It's a newish kind of thing. We'll see how it goes because Julia has also come in with that mindset that proper mathematical array, treating arrays nicely is an important thing to do fundamentally. So they have before somebody says Python, Python has no arrays built into the language, so you bolt them on with NumPy. And so NumPy is nice. It starts to look like you've got arrays and everything, but it's a bolt-on, and as a consequence, it's not integrated into the language. That's true of every language except for Fortran and now Julia. So Fortran remains one of the reasons why all the specs for these parallel programming things are released in C and Fortran. And then C++ is usually kind of an add-on to the C stuff there. Okay. Let's see. Eigen in C++. Eigen the array package. Is that what it is? That's ringing a bell with me. I've used Eigen is the array. Array. Yeah, it's one of several. Yes. Yeah, it's one of several. So this is what I was just saying here. In C++, when you start a project and you know that it's going to be mathematical code, the first thing you do is say, what do I do about arrays? And so there are some prepackaged, there's Eigen, there are a few other options out there as well. And Eigen is actually it's popular, it's used in HPC, that deal with exactly what I'm just talking about. How do we deal with the fact that C arrays and C++ arrays are terrible? And so you bring in a package like that, and sometimes people, so the complaints about Eigen and some of those other packages is that they have some abstractions. They're not super clean in the way that they do the notation, the way you can add things together, the array operations as much as you can do yourself if you limit yourself, if you know you're not going to do everything the same. And so sometimes people instead will strip it back and do their own version. Anyway, it's an open topic. If you Google something like, C, multidimensional C array solutions or libraries or packages, anyway, you'll quickly find yourself in that controversial and contentious thing where people say you should use this package or that, or you should just roll your own because it's so easy to just do a couple of, in C++, it's so easy to define your own objects, you should do your own. And I can tell you large projects that are very well engineered and very important. Some of them use Eigen, some of them use the two other alternatives that are pretty popular, and some of them roll their own from scratch right up Go because it's not that hard to do in C++. So it's so anyway, that all spun off of why is Fortran still around and important to people do under that. And by the way, modern Fortran, as maybe you've gotten to get a hint from what we've done, is nothing like horrible, incredibly crufty old Fortran 77 Fortran. So if you come across that, that is indeed awful, horrible stuff. You hope you don't have to use, even though a lot of the old libraries and whatnot are still written in it because they worked perfectly. They're completely debugged. So nobody wants to go back and mess with them and break them for the sake of making them pretty. But all new code in Fortran from about the late 80s on should look a lot cleaner and more like modern code. And indeed, modern Fortran has objects in it and everything else. Okay, with that, we're well over our time limit for this. We're well into our break. I'd apologize for that, but it's all just Q&A session anyway, so I don't feel like I've been holding anybody up. So we will officially start our break here, and we will be back at the top of the hour and jump into our next topic. I think we are advanced MPI, which is going to be, like I say, hopefully fun to find out all these really nifty features MPI has built into it. That I didn't want to distract you with, but it's neat to find out that they're there. Okay, so I will see you all back here in about 50 minutes. To answer the chat question, of which I'm only seeing chat questions posted in the past couple of minutes. So if you posted something over the interim break, I can't see it. Please repost. It's unlikely it's buffering. Buffering will cause things to get scrambled a little bit in order, maybe take a second or two to get out there, but it won't cause things to just disappear and not come out. I think your code is probably stuck somewhere after that iteration, is my guess. And if you Control-C it, you can break it and see what happens, and anything that is buffered actually will spew out at that point typically, but I think your code's probably stuck after that iteration, and you can put in a few more print statements to try to find out where exactly it's stuck if you want to, or since we're on to it now, you can wait and see how a debugger will allow you to see exactly what's going on. So I will suggest that you pay attention and find out how the debugger works, and you'll be able to see exactly where your code is hung. We'll get to that very shortly. But first, we're going to do some advanced MPI, and I think this will be a fun and interesting topic for those of you that are really now enthusiastic about MPI being a potential tool, because I'm about to show you how MPI just gets easier the more you know about it. There are a lot of pieces of MPI that make life easier on you. I've alluded to a lot of them as we've gone through these exercises so far. None of them have been necessary or that important for the exercises we've done. They would have just confused you with options. But now I think you'll see there are a lot of great options out there. So we're going to go through an awful lot of stuff here, and we'll do it in kind of a collected things together into these families of things working. And you'll see that's how MPI is really organized, is that it's really got a lot of different alternatives for what you want to do to make life easier on you. So even though there are a lot of functions, you don't have to memorize them all or be aware of them all. You'll just kind of find them naturally at hand if you find yourself in those circumstances. The list has grown over the years. MPI has evolved a whole lot since it was first introduced, but it's been a very, very thoughtful evolution. You can see it's not that rapidly paced. MPI hasn't really had any major improvements since 8 years ago. It's because they're not out to just improve, change the standard for the sake of being trendy. It's been very well considered because there's so much important code that's using it and dependent upon it. They don't introduce things that can't be well supported. that don't introduce things that won't be implemented almost immediately. So all the MPI implementations are out there, all support all of these features very well in a very portable manner. So that's not always true of things, even if they are open standards. So we are going to step through these different families. The first thing we're going to talk about are user-defined data types. I've already mentioned them more than a few times as useful things to help us in even the simple problems we've already had at hand, but they can help us in much more complicated problems like we can well imagine our Laplace code or other codes evolving into. So we'll step through it. And that's going to be the second thing here. We really want to define a lot of new message types to allow us to do things besides just send a row of data, which is all we can do right now. But there's also another purpose, which maybe is less important these days, which is that MPI will also do any conversion of data that's necessary. If you build a cluster out of different types of machines and they use different types of data, for example, the most common thing is that some machines use big endian or little endian of data, basically the bit ordering of bytes. It'll do any conversion that's necessary. These days, people tend to build these type of heterogeneous clusters, grabbing a bunch of different types of hardware and sticking together a lot less than they used to. But if you do, it'll take care of that. But this second use right here is the one that most people are interested in. And it's the one that we're going to talk about, and it is basically deciding that we're going to, want to define our own types of messages beyond just a row of ints or a row of floats or the predefined MPI types. It's very easy to do that in MPI. It's got a family of definition functions basically that allow you to start to create or build up any structure, no matter how complicated it is. So no matter what kind of weird, complicated data structure you can envision, you can piece by piece add things together to make whatever you want. And typically that's not what you want to do. Very often you do want to just send a chunk of an array. That's, for a lot of scientific codes, the baseline case. But if you did have something that's very odd, you could build it up with these functions. So you can add these functions together. And the functions that you'll find available are, there's a full list of them on the man pages, but the most important ones are basically to either define a message type that's a contiguous chunk of data. Well, we could already do that with our count type. We could take a contiguous bunch of things in memory and add them together. But if you want to define it in an easier to use way, you could do that. But more importantly, the vector type. Vector type's a very common and popular one, which allows you to start to define something that's distributed, spread around memory in a regular pattern, a vector in memory. So something's got a regular stride. In other words, if you've got an array and the rows are contiguous, the columns are going to be scattered our Laplace code. If the rows in our Laplace code are next to each other from 1 to 1,000, a strip of data, if you want to send a column, then you'd send the first one and then you'd skip 1,000 and send the next one and you'd skip another 1,000. And so we'd have a stride of 1,000 to define that chunk of data. And you might have 1,000 of those with a stride of 1,000, and boom, you've got a column of 1,000 by 1,000 array. So vector is very common and very useful. And we'll find ourselves, you'll find yourself using that a good bit. And in our Laplace code, we could do that. Well, we'll look on the next slide if we wanted to define a row or a column. Indexed allows us to have varying strides. If you got something that's scattered around in an irregular pattern, you can use an index type. Subarrays allow us to send a chunk of subarray of a bigger array. So basically define the corners of the array and you can send that. And you can create a struct of any of these things, in any pieces you want. So that's very general and will allow pretty much you to do anything you want. So once you define the type in MPI, you commit it, and that means it's actually now an official first-class type. And in any MPI routine where it says what's the data type, you can use your new defined data type. Just like you could MPI int, you can stick in your own Joe's data type, and it's perfectly happy to take it. So we'll step through some examples and you can see this in action. So the first example we'll do is we'll go back and look at our Laplace code. One of the first domain decomposition I suggested, which you might want to use a Laplace plate, is to break it up into these 4 squares instead of strips. And I said, well, at the moment, we don't really know how to send a column if it's not adjacent in memory, so we're not going to take this approach. But if we did want to, and we didn't pay a big price for it, by the way, the strips work just fine and they're efficient. But if we did want to break this up into squares, we can easily now, with this vector type, define now a column if we want. So we have a row here, for example, here that is just this straight row right here. And we already know how to do that. So we could send a row if we wanted to. And by the way, the reason we might define a row type at all is because now when we do send the row, you can see instead of having to send 1,000 elements, we can just send 1 row. So even for contiguous data, it's nice sometimes to define things like this. So we send one row. But more interestingly, for our column type that we're defining right here, we say that it's rows wide and it's got a stride of columns. And now we can define it's got a stride, it's a row. Oh, so we're defining this. So it's rows wide and it's got a stride of columns. Yes, so it's this. So this jumps through memory to assemble this so that we're sending it as a column. So this allows us now to have all of our sends and receives basically just say send a row, send a column, and it doesn't matter. So in Fortran, of course, you flip this around because we said it's row major instead of column major, and that's where it's easy to get tripped up if you're flipping between languages. But it's very easy to define rows and columns or diagonals. You can see how you could define a diagonal with a +1 stride if you want. So it's very easy to do this. We can do it here and make our Laplace code with squares work as simply as our current code. So, and again, you can layer these things and add them on top of each other in ways that we can define multiple columns or stripes or whatever we want to do. The index type is useful whenever you've got something that is distributed in an irregular manner through an array in memory. And a good example of this would be a molecular dynamics code. If we've got a molecular dynamics code, which is basically a simulation where you've got a bunch of molecules bouncing around in a space, a good domain decomposition for that might be to break the space up into a bunch of boxes. So this is our real physical box with a bunch of molecules bouncing around in it. And on 9 PEs, we break it up like this into 9 smaller boxes. And each PE is responsible for a space within that box. As the simulation runs, we'll find molecules migrate from one box to the next. And this particular time step here, these 3 molecules are about to move into this box over here. So we want to send a message that contains the information about these 3 molecules. Well, if every box has a particle list with its molecules labeled in it, that's going to have the molecules that are migrating over scattered randomly throughout the list. So if we want to send this as a single message, well, we could go and copy things into a contiguous buffer. We could write a for loop that says, okay, take all these and move them into a single array somewhere and then send that array. But that would waste some extra cycles. Also, it's a little bit of a pain to do. And so MPI gives us a nice message type, this index type, that allows us to just go through an array by pointing it, giving it a list of indices, and it'll go through the array and collect these together into a single message for you. Not only is nicer, it's a little bit cleaner code, but it's also, we're going to find out well, we would find out if we've measured the performance of, and we'll find out as we compare all of these different user-defined data types. It's faster because it saves us the copying. The network interface is happy to go through memory and just grab these things and send it directly. So we're going to find the user-defined data types not only make our code cleaner, but they allow the hardware underneath to do the lifting for us. And it's going to be more efficient than us trying to move things around in memory. So the MPI will go and tell the network interface, just go find these things at this point in memory and send it as a message. Don't waste time copying them all around into some buffer contiguously in memory. And so it'll be faster and cleaner in our code. And we can see how we do this here. Basically, we find all the particles that we want to send. We create this data type. And then we commit it so we can use it, and then we can send. And the data type here is called buffer type. It's this buffer we have down here. So, or buffer of the particles that we construct. So it's this buffer type, and we can send it. And we send it. Now, if you're doing a data type that you're defining every single time step, like every time step, this is going to be a new pointer to a particle list here. It's a new data type every time step. If you do that, you want to make sure you really pay attention to the fact that when you're done with your own user-defined data type, you should free it up. Maybe it's not so important if you're really defining a data type you use through the whole code. If you forgot this, it wouldn't really matter so much. But if you're defining a data type dynamically, like we're doing here, we keep redefining this data type, then you want to free it when you're done. And because this data type, every time around, it can be a different size. It's going to point to different particles. So we create it, and then we free it. And that might seem like that's an expensive operation too. You might say, do I really want to do that? And the answer is yes. MPI makes it very efficient for you to define data types because it's aware of cases like this. It's designed to deal with cases where you define a data type to use basically once, like in this case. With our Laplace code, the data types we define here, we're going to use through the whole code. That's common, but it's also not uncommon to see data types where you use it literally once and then you throw it away. And that's what we do here. And if you do that, you want to make sure you free it up. And MPI is so efficient at defining these data types and quick that it's worth doing that even for one use. On the receive side here, we're receiving our data in as we don't know how many. If you're the receiver here, you don't know how many particles are coming at you. So you don't know the size of that data buffer or anything else. And that's fine because you're going to receive it not as the buffer type that was defined in the other P. Instead, you just receive it as a bunch of individual particles, the particle type, whatever the particle type is that you've got. So we're sending it from this buffer, and it'll be, in this case, 3 it happens to be. But the receiver doesn't know how many are coming in. So could we send a message beforehand with the size of it or something? Yeah, you could do some kind of kludgy thing like that. But instead, the easy and elegant thing in MPI is to say you're just going to receive the particles in as individual particles. So just receive them as a bunch of individual particles. And after we receive it, we can ask for the count on those particles. So that status variable, yesterday, a lot of you were interested in status, which we didn't really need for our exercises, but a few of you were poking around with it. Status, this is where it becomes useful. You can get the count by giving it the message status of the count for that particular message. So we can say receive the message here, and then so that we know how many particles we've got, we can check after we receive it of how many particles there were. Now that sounds well and good, except that what if the particles are varying a tremendous amount in size? If we've got a molecular dynamics code that's larger, sometimes we're receiving 1 particle or none. Other times, theoretically, all the particles theoretically in the entire simulation might be coming at you. And so it's kind of wasteful, and it might even be impossible to anticipate the worst case scenario by having a buffer that's big enough to receive the incoming particles. And so right now, that's what we did here. We assumed some maximum number. We might have said this is 100. And so when we receive the particles, we have space for 100 particles here, but then we find out we only received 3. But maybe, like I said, it's not a reasonable way to go. You don't know what the maximum ceiling is. You don't want to commit to one, and it would be unsafe to do so. And then in that case, you want to have dynamically allocated buffers. This is a very common thing to have dynamically allocated stuff in real codes. You really want to size things appropriately as you go along. Your data structures to begin with. Our Laplace code, if it was a real Laplace code, it would let the user input the size of the array. It wouldn't be hard coded in. So dynamically sized data is very common. And in our case, we can deal with this very straightforward. We can check the size of the message before we even receive it. So there's a call called MPI probe. If you want to see a message while it's still in your receive buffer, before you've even received it into your regular memory, you can do that. We can probe a message. And when we probe a message, it just says, okay, are there any messages coming for me from this PE with this tag? So you still filter the messages. You say, this is the message I'm interested in seeing. And if there is a message like that, then the status that comes back will let us check the size of the message. So now we can see how many there are. So we haven't really received the message yet into our memory, but we can see that there's a message waiting for us with 3 particles. Now we can actually do our regular C memory allocation or Fortran, do an allocatable data structure. Now that we've got it, we can do it. Oh, by the way, MPI also is aware of the fact that things in regular computing languages, when you have a particle, when you have a type of some message, if it's a structure, we'll talk about this a little bit in the next slide or two. We'll talk about structures. The size of something might actually vary from one implementation to the next, depending on the way things are padded and bounded and everything else. So MPI will actually do a nice conversion of the number of bytes that you really need for a message. So we can check the actual extent, the real byte size of this message, and now we can allocate for it. We can say we have this many messages that are this particular size because of the data type that's involved. We've now got a buffer in memory that we can receive the particle into, and it's exactly the right size for 3 particles this time around. And we can free this up when we're done with it. And the next time we've got 100 particles coming in, we can have a buffer that's that size. So MPI makes it very easy to deal with, the real world case of varying message sizes from one iteration to the next. So let me see, we got some questions here. Let's confirm. Stride skips between certain elements when defining a vector. Yes, so stride is a fairly common term you'll hear used whenever you're dealing with things that are spaced through memory in a regular fashion, whether an MPI or anything else. So the stride of something is just how regularly far apart it is in memory, and 2-dimensional or highly dimensional arrays, higher dimensional arrays in any computer language start to have a stride. You got the first dimension, things are contiguous, then the next dimension, they'll hop around, maybe 1,000 at a time. If it's 3-dimensional, then you've got another stride that's bigger to go in this direction. Things might be 1,000,000 apart in 1,000 by 1,000 by 1,000 array in the 3rd dimension. So that's the stride. And by picking the right stride, we can pick which dimension we're moving along when we define the message. Percenting columns would be fastest, triple sent in the stride. Strides to make it faster. No, it's all going to be the same. If you've got something that's contiguous in memory, you know, defining it or sending a count for it's going to be roughly the same performance. So you don't have to worry about that. It just cleans up the code a little bit even to be able to send one row instead of pointing at the beginning and giving an account. But they're both going to be the same performance roughly. In case like the MD example, does the parallelization induce a constraint on a time step to avoid a particle crossing multiple cells? Oh yeah, so yeah, not to get too involved in particle simulation codes, but yes, this particular algorithm to deal with molecular dynamics like this, you do have some constraints, like you want to make sure your time step is small enough that particles could never jump a whole box, for example. And usually that's not a problem because in real particle dynamics, you actually want to make sure your time step is small enough that particles can't just skip right by each other, even within a box. So usually within a real particle dynamics code, you might have some small subgrid within here, and you might make sure that the force between your particles if it's defined in a certain way, say it's a Leonard-Jones potential, that your smaller boxes in here to keep track of which molecules are next to each other are the right size, and that'll be the size of your ghost zone. And so you'll have a Verlet list to keep track of all the local molecules. So there's a lot of details to making this work right. But yes, one of those is that you got to make sure your molecules from one time step to the next aren't moving in big chunks and can't just skip whole zones. As a matter of fact, you want to make sure they're moving slow enough time step they can't just even skip by each other within a box. So yeah, that's one of the details of molecular dynamics simulations. Okay, dynamic memory is, like I said, a standard thing in lots of codes, and you might even find yourself with some kind of linked list where you've got things scattered all over memory. So it's not just that they're in an array and they're scattered to an array with regular indices. You might have things scattered all over memory to where you need to send point at a bunch of different, give it a bunch of different memory pointers, basically. Give it a list of memory pointers to be able to gather your data together again. It's not an uncommon thing at all in a real serious code. And so we have the ability to do that with MPI-2. We can give it a list of pointers, basically memory pointers, in order for it to collect things. In MPI, things that are addresses, basically memory pointers, are of the MPI-A-int type. So this basically says this is a bunch of memory pointers. It's the proper type for it. And this displacements we're going to send to our create are basically a bunch of memory pointers. So then somewhere in our code, we can have a while loop that goes through our list and decides which things we're going to send. And it's basically collecting all the raw memory pointers to things in our list. And when we're done, we can create a type that we basically pointed at that list of displacements. And now when we send the message, we commit it, we send the message, it's happy to go through memory itself and grab all those things together. So the pointer, we don't point it at a buffer, we just point it at the bottom of the memory, and we say we have one of this type of message, this item's message type. And it's a bunch of memory pointers. And it'll go along and collect all of those things from memory and turn it into a nice single message to send. And when we're done, we need to free it again because this is the kind of thing we're doing dynamically as we go. We're defining this message almost every loop of this code. But this works just fine. This is not uncommon. You could also decide that you want to hand pack a bunch of different data types together. You don't want to build up a data type using all the hierarchy of commits that we could do. Instead, you say, I just got a bunch of different data. I want to cram them all in the message. And we can do that. We can just pack a bunch of messages into an MPI message and then send it as an MPI packed type. So this is a predefined type that says this message just has a bunch of things we crammed in here. And that's fine. And when we go to receive that, we receive it on the other side. We don't know how many things are packed in there, so we get to count for it. And then we can unpack a bunch of things from the message. And when we unpack things, we get this pointer variable that says what the next thing is that it's unpacking, and it'll automatically update itself every time we unpack a message. And so we can unpack all the individual pieces, and or we could just grab them all at once if we want to just get the count on them. And we can even mix types when we do this. So we can take a combination of types. For example, if you've got a C structure, it may very well have an integer in there and a character and double and we can pack them individually. So here we pack, matter of fact, 10 integers. Pack 10 integers here and a string and this double and these 10 integers here. So we pack a bunch of things in here. And on the other side, when we do the unpack, we need to pay attention. We need to unpack them in the same order that we pack them. So that's easy enough to do and as flexible as you can want. So you can put anything you want into an individual message. But you might say, well, can't I just send the structure as a single thing? And indeed, you can do that. You don't have to hand pack it. But when you do that, you have to pay attention a little bit to the fact that structures and this is true pretty much of any defined data type in any language, have padding going on. There's a little stuff going on behind the scenes because modern processors like data to be aligned on certain boundaries. So even though we count memory as byte 0, byte 1, byte 2, processors don't really like, and memory management systems don't really like if things are just scattered around willy-nilly. So they'll usually, unless you override things, most computer languages will take and pad things out a little bit to keep them on byte boundaries. So in other words, this C structure right here, it's a character, you might think that's 1 byte, an integer, you might think that's 4 bytes, a double, you might think that's 8 bytes, right? So if we add it together, we might think this is 13 bytes. But if you actually look at the size of this, and this isn't an MPI thing, it's just a language thing, it's probably at least 16 bytes. It probably padded this out a little bit and padded this out a little bit, kept them on 4 byte boundaries or something. And it's very language and platform dependent, what exactly it's doing. But it's unlikely that this is 13 bytes, even though that's what makes this up. And so MPI is perfectly capable of dealing with that. So it has the ability for you to get the extent of the things the structures that you're packing. And so it knows how to pack them appropriately into a message and how to, more importantly, unpack them on the other side so that it's compatible with what the compiler is actually building. And so this is pretty straightforward to do, but you do have to pay attention to the details. But MPI gives you the tool to do that. And that's if you just want to deal with the raw structs, which again is not an unreasonable thing to want to do. As I've said, the data types, not only you can see clean up your code and make life a lot easier to deal with things like surfaces in a three-dimensional Laplace code, or even in our current one if we want to send rows and columns, but they speed up the code. So they're there for convenience, they're there for efficiency, and you should right off the bat grab them and adopt them the first time you find yourself moving things around to pack them into a message in MPI. Go, I don't want to do this. I'm just going to define this data type and let MPI do the heavy lifting. Okay, let's see what we got for questions here. We need to know the size for sending the data as well, right? How can we deal with that if it's totally random? Well, the size, when you define the message, you're defining as a type, the type knows the size. So here, for example, where were we doing this dynamic memory thing? So here, for example, when we send the message, we're sending one of the type. So when you do a user-defined type, the size is going to be, well, typically one of something. I mean, you can choose to define a type and then send multiple copies of it. That's fine too. But the type size is one because the type knows the size. So this size is varying all over the place, but it's contained in the type. So the type knows the size, and when it's send time, you're sending one of the type, even though the type has different size. And we can see that with this buffer type here. Where's the send here? We create the type, and the send is one of this buffer type. So the buffer type knows it's 3 of these things, but we only send one of it. So that is, on the other hand, when we receive it on the other side, if we receive it as individual particles, which is what we do, then the count is going to say 3 here, because it's going to be 3 particles, which is exactly what you probably want in your code. Okay, let's see. Does MPI status automatically reduce the size and the status count based on bytes and size of data structure, array of pointer? MPI is, well, it's behind the curtains kind of thing. So I would hesitate to say without staring directly at the source code, but it's certainly, given that it knows the data type and given that it knows the size of the message it received, it can figure out the count right there from that. So that's the math that's available to it. How exactly it chooses to go and pick that apart, I can't say without looking at the source code, but that's pretty straightforward. So I'm missing something. How is sending data with indices with non-contiguous data as efficient compared to doing the same thing with serial code, where iterating over non-contiguous data is not efficient? The main thing, so if we've got non-contiguous thing in memory, I'm not saying this is as fast as if it was contiguous. That's not, it's always best if things are contiguous. What I am saying is that given that it is non-contiguous, we can't help that. That's the algorithm, right? The molecules are where they happen to be in this list. Given that it's non-contiguous, what I am saying is that it is faster, or at least as fast, for us to just send to MPI these pointers and say, you go collect it yourself, as opposed to us writing a separate little piece of code that goes and copies these into a contiguous buffer ourselves and then says, send this message as a contiguous memory. I'm saying MPI is faster at collecting things contiguously in the network interface and sending them than we would be writing a separate code. But the ideal case is always, you're always sending contiguous messages. So yes, it would be nicest if we always were just sending 1, 2, and 3, and that's going to be fastest. But that's not the reality of the data we've got. The data we've got is distributed around. So given that it's distributed around, letting MPI do the collecting is going to be faster than you collecting it into a contiguous piece yourself. That's what I'm saying. Okay. Is this specific to C, or are there Fortran equivalents of dynamic memory related? Yes, Fortran has allocatable memory. Fortran is quite happy, as a matter of fact, in many senses, even cleaner to deal with allocatable data types. So yes, the Fortran equivalents are exactly the same in functionality with allocatable data. So if you're using Fortran, and you should be using allocatable data whenever you see these kind of things. Okay. So much for user-defined data types. I hope you can see the elegance and the power of that. Let's move on to another thing that I've alluded to briefly, but we haven't really gotten into, which is collective communications. There are a lot more options than the things we've been using so far, which is broadcast and reduce, basically. For example, an operation that many of you will find yourself wanting to do at some point in time as you write algorithms is that one of the PEs, we'll say PE0, since it's often the manager PE and it often has some special data, wants to send data to all the other PEs, but not the same data. If it was the same data, if we wanted to send all this data to all the PEs, we could just use a bcast, right, to broadcast it. But instead, you want to distribute the data around. And so PE1 gets this and PE2 gets this. This is a common enough thing to do, and there's a routine to do it called scatter, to do it in one fell swoop for us. We, of course, could do this ourselves with point-to-point message passing and a loop that goes through here, but scatter will do it all at once for us. And so scatter, you point at the beginning of the buffer and you tell it, how many things and what kind of strides they have. So we can, scatter gives you the ability to say we can send 2 things to each PE, and we can do all kinds of different variations on this. I'll talk about a few of those in a few slides, but the basic notion of scatter is this. We've got one chunk of data that you want to distribute to all the PEs. And the converse of scatter is one that you also will stumble upon quite often. All the PEs have some chunk of data you want to combine back together. You don't want to reduce it down to a single piece of data. We know how to do reduce. Instead, we want to collect it into one place. We don't want to combine it. We just want to collect it. And so that's where gather comes in. And gather allows one of the PEs, very often might be PE0, to gather all the data from other PEs into a single array. And there are a lot of variations on this because they are necessary. They're very, very useful when you start actually writing real algorithms and real code. For example, you could have an irregular pattern for these operations. You might want to scatter 3 elements to PE1 and then the next 2 to PE0 and none to PE3. So if we did an irregular thing, we can do that. And that would be scatter V. The V stands for vector types because you then, one of the arguments of this is an additional vector, an additional array that gives that pattern of irregular data that you want to scatter. So there are V versions of a lot of MPI routines. And whenever you see a V version, it basically means it's doing an irregular pattern. And to define that pattern, you give it an additional argument of vector. A vector, so the first entry in the vector says how many go to PE0, the next entry and it says how many go to PE1, and we can do a very, very irregular pattern, both for scatter as well as gather. We might want to gather 1 element from PE1 and 6 from PE2, and we can specify that with a gather V. There are also W versions of these things, which mean the results are returned to all the processes instead of just the root. So a lot of times you want to gather this data together and collect it in an array, but you then need all the PEs to do it. We could very easily do that ourselves by gathering it and then doing a broadcast. We've already kind of done some tricks like that where PE0 gathered some data and then broadcast it to the rest of the PEs. We could do that, but it's more efficient and also nicer in your code to use the or to use the all versions. And the all versions will basically make sure that all the PEs get the result. As a matter of fact, I already mentioned reduce all allows the reduce to not just go to PE0 or the root PE, but all the PEs get the result of the reduction. It saves you the extra broadcast afterwards. And again, a little cleaner in your code, and also MPI will do it more efficiently behind the scenes than as 2 separate operations. So there are variations on all these kind of things. And there are some advanced versions of all these things. We can have reduce operate on not just on individual values, but arrays of data. You can do, for your reduction operations, user-defined reductions. MPI has a number of them already defined. We've been using sum and min and max, and there are a bunch of other predefined ones. But if that's not enough for you, you can define your own reduction operation, combine data in any way that you want. You can do things like if you do a min or max, you might want to find out where those things are actually located. Which one was the min and max? So there are lots of extensions and things on all these routines. If you find yourself having to write your own thing and you say, I wish MPI had a version of this, take a quick look at that family of routines and make sure it isn't already there. As I said, all reduce is one that we've already mentioned where it's a reduce, but all of them get the results instead of just P0. You might find this useful even in the Laplace code we're doing right now. So there are lots of variations on these things. I don't go through them all. I won't go through all of them in the manual, but they're there for your convenience. You could always write them yourself with the tools that you already have, but an MPI has them that not only make life easy for you, but they're usually the most efficient implementation of all of those. So that's kind of the collective family of operations. Let's see. Use scatter model to solve the Laplace exercise. Scatter doesn't really have an obvious role in the Laplace code that we're doing right now. So I think the answer is no. There's not really an obvious role in the Laplace code right here. Okay, communicators and topology. So far, the communicator is a thing that we've just completely kind of ignored. I just said we're using the world communicator everywhere, but I kept assuring you that it has a lot of uses as your codes get more complex. In particular, so we could break PEs into different groups. And now we're about to see some of those many uses. And it is important because we find ourselves right now doing any of the collective operations have communicators. So when we do a collective operation, all of these and other collective operations as well, sometimes you don't want all of the PEs to participate in those operations, but it's a problem if all you had was MPI-com world. We know, let's take the simplest collective operation of all, barrier, right? Barrier says all the PEs need to get here before anything can continue. Well, sometimes maybe you have some of the PEs off doing other things. They can't participate in the barrier, but you'd like to have the other PEs participate in the barrier. Well, you got a problem if all you had was MPI-com world. Your code would just hang when the other PEs that are off in some other subroutine where they're supposed to be don't participate. So by having communicators now, wherever we have the world communicator, we can now split PEs so they can do different things. We're not just always tied into it. So we can have groups of PEs doing different things. We're also going to find out that the communicators will help us with topologies where we start doing a domain decomposition in our code. The communicators can help us manage that. That'll be clear from the examples. But we'll also find that they're useful whenever you want to have an MPI library, for example, some subroutine that a bunch of PEs can call. Well, the PEs that call that subroutine go off and they're in that black box of the library doing their own thing. That library might have inside of it a bunch of collective operations like barriers and reduces. Well, the PEs that are in that library should be on their own. They shouldn't have, if they call a barrier inside that library, the PEs that haven't called that library will get messed up. They'll get hung if there's a barrier in the library and they're not participating. So to have some of the PEs go and branch off and participate in their own control flow for a library, we need to break them off and have them have their own communicator, their own way to deal with collectives and barriers and reduces within the library and not affect the other PEs. So anyway, we'll step through a few of these. First of all, though, how do you make your own communicator? MPI has two basic ways to do it, and they're both very simple and friendly and straightforward. The first way involves groups. MPI has some routines that allow us to manipulate with some basic set operations the groups that we have. So I'll just go through the example because it's the easiest way to describe it here. So in this case right here, we have a reduce operation that we would like just the worker PEs to participate in, not PE0. Maybe PE0 is busy getting some input from the user or whatever. We just want the workers to participate in a reduce operation. Well, if we only had MPI-com world, we would have a problem. We could never write a statement like this, like if I'm not PE0, do a reduce. Because if we had com world as the communicator here, when they go to do this reduce operation, they're going to sit here and hang waiting for PE0 to chime in too, because that's what com world would do. So any collective operation wants all the PEs in that communicator to participate. So if our only communicator was com world, we could never have a piece of code like this. So we want this piece of code though. We want all the PEs to do this reduce except for PE0. It means we need to have a special communicator, this workers communicator. Well, here's how easy it is to define that with groups. First of all, we grab a group to start with from com world. So you got to grab a starting group. And since we don't have any groups yet in this code, com world is a good place to start. So this will create a group from an existing communicator. So we grab the com world communicator, all the PEs, and we create a group. And then we want to create a group that doesn't have PE0. So we want to find from our list on the next slide of group manipulation routines, and they're all the basic operations, we want to use an exclude on this group. So we want to exclude one PE from this group. So we exclude this PE here. It's in this list right here. Our list only has PE0 in it. We exclude PE0 from the group. So now we have a new group. And we can continue to manipulate that group. We can come up with any group we want with those group manipulation operations, but we're going to just be happy with this one. That's all the PEs except for PE0. Once we got a group we're happy with, we create a communicator from that group. And now here we have a new communicator, COM workers, that's just the workers. And now we can do things like this. We can branch off to where just the workers are using collective operations. And now they can call the reduce and everything works fine. It won't hang. After this operation, we can still do a reduce with PE0 if we want, but now we can use the world communicator. But we can't use the world communicator in here, it would hang. So this is how easy it is to manipulate the groups and create a new communicator. And when we're done, we should free the group up, especially if we're doing this dynamically. Maybe this is used for the whole code, nobody cares. But if we're doing this over and over, we want to free the group when we're done. So this is a very straightforward way to do that. And again, the group commands are all the basic things that you want to do. You should have no problem creating a group and shaping it in any way that you want. Let's see, we have some questions here. Can you please explain the difference between all gather and all gather V? Okay, I'll take a, oh, well, I don't need to go back for that. Gather gathers things in a regular pattern. It might grab one thing from PE1, one thing from PE2, one thing from PE3. But what if you want to gather things in a regular pattern? You want to grab 3 from PE1 and 4 from PE2 and none from PE3. You can do that, but you have to then give gather a list of how many you want to grab from each PE. And so that's what gather V is. Gather V adds in one more parameter, that vector. You give it a list and say how many you want to collect from each one of the PEs. So that's what the vector version is. Doesn't the use of correct group take care of the if clause already? Nope, nope, it does not. So that's a good question here. So since we have the correct group in here, what if we get rid of the if clause? Well, if we get rid of the if clause, PE0 is going to come down here and still think it has something to do here. It doesn't have, it's got this COM workers group too. It just doesn't belong to it. It's going to want to participate. So no, so the groups don't give us the ability to skip this. We still need to make sure any collective, all the PEs are going to want to participate in it. It's that simple. Anytime you have a collective operation, so you do need to pair it off. But that's a reasonable expectation. That's just not the way MPI will work. Okay, the other way I said we have 2 ways to deal with creating our own communicators. And there's another way, which at other times can be much more convenient and easy to do. It makes sense. And that is to take an existing communicator and break it up into pieces. So if we want to take an existing communicator and break it up into multiple pieces, we can do that with COM split. So it's pretty powerful because it can do a whole lot of stuff in one fell swoop if we set it up right. So COM split has as its most important parameter this color key. That's what it's usually called, this parameter, color. And the color parameter, it means we can assign different PEs different colors. And then they all call COM split. And when they walk away from COM split, they're all going to end up with a different communicator, each for their own color. And so this is a way to break things up into kind of any complex pattern you want, just by in advance, making sure you assign color to things. So in our previous code, for example, we could, instead of what we did to come up with our COM workers communicator, we could do this. We could say if our PE0 color is equal to 0, all the other PEs get a color equal to 1. And then they all call COM split, and when they walk away from it, the other PEs have a communicator of a color, I should say. They have a separate communicator. So I shouldn't overcomplicate this. They all have separate communicators. They're going to have the same name for it. So PE0 actually has a communicator called COM workers, but you wouldn't use it. And it's a separate, it's got a different value than the communicator that all the workers have. So we could stick this in the previous code and it'll work. The other parameter here, I guess I don't have it on the slide, is the key. Oh, I do have it up here, is the key. We could actually even control in the new communicator the ordering of the ranks. Every time you make a new communicator, within that new communicator, the PEs also have their own new numbering scheme. So if we take our PEs and we break with our weather code, if we break our PEs into ocean PEs and land PEs, each one of those communicators, the ocean and the land ones, still start at PE0. We now have 2 PE0s. We have a PE0 when you're using that communicator. So within each communicator, any communicator you make, that smaller subset has its own listing from 0 to whatever. So if we break our weather code into 1,000 land PEs and 500 ocean PEs, when we use the land communicator, the PEs are going to be numbered 0 to 999. When you use the ocean PE communicator, those PEs are going to be 0 to 499. So there's new numbering, always contiguous within each new communicator. You can, if you want to, if you don't do anything, it's going to be more or less randomly assigned. You don't worry about it. It'll probably inherit from the previous communicator, but you can think of it as randomly assigned. If you want to control that, the key allows you to control that. So if you really want to control exactly what the new PE numbering scheme is in a new communicator, you can do that as well. So ComSplit is very powerful as long as you set up the color and the key in advance. You call ComSplit and boom, you've got a bunch of communicators, as many as you want, each ordered however you want. Okay, let's see this. Okay, so much for that. Okay, topologies. Communicators also allow us to deal with, the topologies that we find so useful and so powerful here with what we're doing. Even with our Laplace code, we have to worry about, so I should say topology, meaning kind of the spatial relationship between everything that we're doing here. So with our Laplace code, we've got the strips related to each other, and we're bookkeeping ourselves. We're just knowing that PE2 should send up to PE3, and PE3 should send down to PE2, and it's no big deal with our simple code. But as life gets to be more complicated with one of our meshes, our tetrahedral meshes and its weird shapes, you might not want to be responsible for that bookkeeping. And in the earlier days of MPI, people pretty much did make sure they did all the bookkeeping themselves. And as a matter of fact, the Hercules code we were talking about earlier, that's the case. But that's a lot of bookkeeping. And if MPI could do that for you, it might be nice. Well, MPI can offload some of that for you. So the data decomposition can be captured basically by the topologies, and we're going to look at it. And first of all, we'll look at the Cartesian topology routines, which basically allow you to capture any kind of nice rectilinear relationship like we have in our Laplace code. But sometimes life isn't so rectilinear, in which case, like with our tetrahedral mesh version of codes, we can have a graph topology, very general. So let's take a look at the Cartesian topology and how that's captured. So here is a grid, a nice simple grid like we might use with our Laplace code if we expand it up to run on a lot more PEs. So our code here in this case is a 5x4 grid, and we could keep track of this. We have no problem keeping track of all the mathematics ourselves and doing the bookkeeping. However, MPI says we can create a communicator that's aware of this and will manage all of the appropriate directions for messages and whatnot. It's very simple. So with the Cartesian create command, we're going to make a new communicator here, and all we need to tell it are dimensions. In our case, we've got two-dimensional problem that's 5x4. It could be periodic. So a lot of problems are periodic. If things wrap off this end, they come back here. Ours isn't periodic here. So once we define that, we can create this communicator, and it now knows how things are related to each other. And we'll see how we exploit that in the next slide. But this communicator now is aware that this is what we're trying to do. Now, it can go ahead, as a matter of fact, it will even do nifty things. Well, we'll see how like com null and whatnot will work in a slide. First, let me show you how you actually use this now. Now, when it comes time to do our message passing, we can ask MPI. We can say, hey, who is our neighbor to the left and to the right? And there are routines to allow you to query that kind of information. I'll give you the short list of them. For example, the shift command says if I want to shift data to the left or the right or up or down or whatever, who are my neighbors? What's my source and destination? So with the Cartesian shift command, you can query that kind of information. Here in our case, we're saying we want to ask for our 2D communicator that we just defined on the previous slide. We want to find out who our neighbors are in this axis right here. And this will tell us that, so if we send information, if we shift the information on the 0th axis, so this is basically just numbering our dimensions. On the x-axis, if we want to send that information in the down direction, who is our source and who is our destination? Well, it's message passing time. And so for this PE right here, when it calls Cartesian shift, it will come back and it will automatically have assigned the right destination and the right source. And that's nice. It will do that simultaneously for all the PEs that call this. We'll all get the right answers. And it will even do nifty things like on the edge here, it will find out the destination will be MPI-proc null, will automatically get assigned to it. So we can have a nice loop that just says everybody send to the left, and this one will automatically send to what it thinks its destination is, which would be proc null. It's just fine. It's going to send it into this black hole, and everything will work fine. So the earlier question, going back to the question for lunch, where somebody asked a very sensible question, is MPI going to have a lot of conditionals, a lot of logic required for this message passing? And I said, well, it could, but MPI can also absorb a lot of it. We can see right here, this kind of command means now at message passing time, we just do sends and receives. And it took care of all that logic about things on the edge, who's up, who's down, left, right. It all gets sucked right into the communicator and the routines that work with the communicator. It makes life much easier. And there are other routines you can use then to find information from the communicators too. To find out, you can even find out what planes you're on, for example, if you are dealing with operations that work within planes like FFTs or something, you can find out who's in your plane. Anyway, there's a handful of operations that give you just about anything you could want to know. So it will make your bookkeeping much simpler. But as I said, the world isn't always Cartesian. You might have things that are much less regular. And the graph topologies, or the graph topologies and graph communicators allow us to deal with very irregular things. When I say graph, immediately you probably think of something that's very irregular like this, but it can even be something that's pretty regular, but not quite exactly Cartesian. Like our Laplace code, maybe we care about the diagonal elements. We don't. In our code, for any given point, we only care about up, down, left, right. But what if we cared about diagonal elements? Well, then maybe we could, use a graph to connect things up in a still regular fashion, but still something that's not strictly Cartesian. So anyway, we have the ability to do anything from uber flexible to pretty regular with the Cartesian, with the graph topologies. And there are a couple of different graph topology options available for you. There's an old one that nobody uses anymore, I won't talk about. Instead, the adjacent graph interfaces and the general graph interfaces are the ones you're likely going to find. The only difference between them two is one assumes that the PEs have information about their neighbors, and the other one assumes that maybe the information about who your neighbors are is not scattered around regularly. Let me show you what I mean by that. So here's the adjacent graph interface. It basically allows every PE to define, when you define the communicator, when you create the communicator, it's going to allow all the PEs to define who their neighbors are. So if we have a graph that looks like this, for example, PE1 here has no neighbor sending information to it. It has one neighbor that's sending information to, and that happens to be 3. PE4 here, for example, has one neighbor sending information to it, 3. It has one neighbor it's sending information to, 0. So in this thing right here, we've defined completely how our graph is set up. Each PE knows who its neighbors are. And if we call this now, we're going to create a communicator that's aware of all of this organization. You can even include weights. Sometimes networks, you care about weights, the strength of a connection. So this right here allows us to have each neighbor define who its neighbors are at one point, and from there on out, the communicator takes care of all of that. Now, sometimes the PEs might not know to start with when it's time to define a communicator who their neighbors are, because that whole meshing and domain decomposition to partition your mesh can be complicated. And so maybe only some of the PEs know who the neighbors are. That's fine too. That's the general graph interface. That allows PE0 here to start defining, and PE4 to define the network for everybody. So PE0 and PE4 here define the entire network. So PE3 doesn't know who its neighbors are, but by the time we're done with this, the communicator will capture that information. So it's basically sometimes the PEs don't know their neighbors when it's time to create the network, and you can let them know who their neighbors are. Once you've got this done, now the communicator for this is very, very powerful. You can do things like find out who all of your neighbors are, and the PEs can find out who their neighbors are assigned to, and things like that. But more importantly is when you actually go to use these things with the communication. So once you set up this graph communicator, you can do in one fell swoop an awful lot of mighty complicated communications. So for example, here, the neighbor all gather routine. Once we've set up our graph communicator, so this communicator, we set it up previously and all the PEs have their neighbors defined, we can with one call have each one of the PEs simultaneously broadcast to all of its appropriate neighbors, and only its appropriate neighbors, information. So it's like doing all the individual point-to-point sends. This will send information to all of your neighbors at once. And so this is basically replaces a whole complicated loop of you saying, who are my neighbors? And now I need to send this message to this neighbor, this message to this neighbor, this message to this neighbor. This will do it all at once. This will do different messages to each one of your neighbors all at once. So the reason you go to the trouble to set up these graph topologies is now when it's time then in your code to exchange, do your ghost zone exchange with your neighbors, for example, instead of all the complicated logic of each PE has to figure out who its neighbors are and might have different numbers of neighbors and different things it wants to send. Now in one call, we can do all of that exchanging with our neighbors. We can do our ghost zone exchange in one call with a very, very irregular lists of neighbors. So that's the real power of this. Is our communicator has everything it needs to know, do all the message passing in one call. And things can even get more collective. You might want to say, for example, every neighbor gets different types of messages. We're not doing that with our Laplace code or a lot of Halo exchanges, but if I want different message types going to every neighbor, I can do that as well. So you can get you can basically accommodate any situation once you've set up the communicator to capture who your neighbors are. You can now, with one call, do all of those exchanges. And again, even for very irregular patterns. And so that's where these kind of problems become much, much, much more elegant than if we had to do all the bookkeeping ourselves. So let's see, you can create groups, collective. I won't even get into this. This is kind of, I should probably get rid of that. It's esoteric. None of you will use that. So basically, communicators allow us to have our code flow be whatever we want, even though collective operations demand that everybody in the communicator participate. That's fine. We can define the group that should participate. They make life easier for us to not have to write complicated send loops to send information out. They make it easy for us to collect all the bookkeeping of how neighbors are related to each other into one place. So they're very powerful. And now you can see where COM world was fine for everything we did so far, but as soon as your code gets more complicated, you'd find COM world to be limiting. Okay, so let's see what questions we happen to have piled up here. Different communicators have the same name. How do collective MPI operate different between them? They have the same name, but they have different values on different PEs. So in other words, it's like saying the variable X on different PEs. They're all called X on all the PEs, but they all have different values. So if we break a communicator into two, say we have a communicator we have 1,000 PEs, and we make a communicator for PEs less than 500 and more than 500, right? That communicator could be called my communicator, but the one on the less than 500 PEs actually has the value that means that, it's got some mysterious magical integer or whatever assigned to it, whatever value MPI uses to tag it. It's got a handle, is probably the way most programmers call it. The handle for that is different than the value or the handle for the communicator that's top 500 PEs. So just like we could have a value X, all the bottom 500 PEs could have the value X equals 0. The top 500 PEs have the value X equals 12. Well, they're both the variable X, but they're different values. So the communicator, your code calls the communicator, split communicator when I split things in two. But the value of the split communicator is different for the bottom 500 PEs than it is for the top 500 PEs. So when you use that communicator to call an MPI reduce routine on the bottom 500 PEs, it's called split communicator, but its value says, hey, only use these PEs. When your same code might use that call a communicator with split PE on the top 500 PEs, but the value assigned on those top 500 PEs is different. So the name of your variable name for the communicator is not its value. The value of the communicator is what has all the magic information. Is there a built-in polar coordinate communicator? There is not. So polar coordinates are very important and widely used. You would have to define that yourself, but that's where the graph communicator says you do all that pain once. You have a part of your code that sets all that once up and says, for my polar coordinates, this is the way things are distributed. And then once you do all that in one tiny part of your code somewhere, you take care of that painful math, boom, now your communicator has that information. But there's no built-in one to do that. This is called to be executed on all PEs. Yes, so communicator is itself a collective operation. So all of PEs that are going to be affected by that call need to collectively call it. So communicator is a collective, and just like any other collective, anything that's involved. So if we're starting with the world communicator, all of PEs need to call that communicator, and they might walk away with different new subcommunicators, but they all need to call that. Now, if you've got a subcommunicator, actually technically only the ones in that subcommunicator, if you want to split that up, you need to call that communicator create routine. But communicator is a collective. That's why it has a communicator as one of its parameters, and any collective, everybody has to participate in it or the code will hang. Okay. So much for communicators. And boy, we are not getting through these slides. We have time this afternoon, so we're going to run a little bit behind schedule because we have a lot to cover here. But the advanced stuff's the most important stuff, so no problem. We're gonna finish on time today. We're going slow here. Another very important thing that we kept coming back to was the fact that our basic blocking MPI message passing works great to get a code off the ground. It's very friendly to write and debug a code, but it has some pitfalls. It has some performance limitations. It could potentially deadlock. So this standard way we've been doing all of our message passing, right, where we do a send and it copies to a buffer and it sends it to a receive buffer and then a receive reads it in, you said, it has some limitations. And I assured you that non-blocking receives make all this go away. And indeed they do. It's very easy to do to change your code into non-blocking receives. So in other words, if we got a piece of code like this with our blocking, since we just talked about this right before the lunch break, I won't reiterate these slides. Since with our Laplace code, we could theoretically block. We just went through these slides. I said, you don't want to do this, you want to do that, and blah, blah, blah. But mostly, I don't want to think about this blocking stuff. I don't want to think about how this happens. So this is exactly what we covered before lunch, same slides. I don't want to think about all this stuff. Instead, I just want to move to non-blocking. Actually, for this very limited case, there's an MPI routine called send receive that some of you might even use that just exchanges information in one fell swoop with send receive. So for codes like the Laplace code, this is actually not a terrible way to go. But the more general answer is to go with non-blocking routines. So here's a nice generic way that we don't ever have to worry about things backing up with our sends and blocking and things having to be sliced up. And the non-blocking routines are very similar to our regular send and receive routines. The one difference being that the request flag, there's an extra parameter on the end, is necessary because they're never going to block, but we need to then check and make sure that the data was actually sent before we go and mess with it. So if we send data, it might not send immediately because it's not making all these extra copies for us, but if it's not sent yet, we shouldn't mess with the variable we're sending, or else we're messing with data that should have been on its way already. So the way we can do that, the way we can keep ourselves from messing with data, is we can check this request flag, which will change after the data is set. We can say, now we can mess with that data. Likewise, when we do a receive, a non-blocking receive will never block, even if the message isn't there yet. So if the message is there, it's basically a regular receive. But if the message isn't there, it won't block. It'll continue on its way. What does that mean? It means you didn't receive any meaningful information yet. So you shouldn't try to use the data yet. You wait until the request flag changes and says, yep, that message came in. And then you can use the data. So how do we wait? Well, we can use either the test or the wait routines here to see if it's time to wait. If you use a test routine, that can be in your own code. You could say, has it come in yet? No, continue on my way. Or you can just simply say, hey, I need this data before I continue. I'm just going to sit here and wait. So you can look and see if it came in yet, or you can just block until it comes in yet. But you need to take responsibility for that if you use the non-blocking routines. We'll see them in action in the next slide. And there are variations on this. You can wait for some combination of messages. If you have a lot of messages outstanding, right? Very often our MPI codes, you've got more than one message flying around. Like in our Laplace code, we might be receiving data from our neighbors to the left and to the right. So we can wait on some of those messages or all the messages or some combination that we pick of things that we want to check and wait on. Here's how we basically do non-blocking with our shifter exercise from yesterday. And it's very simple. So our regular shifter exercise that we had yesterday, we wanted to send messages up to the next PE. So in this case, instead of using sends and receives, I use I receives and I sends. So here I say I want to receive a message from my, my next neighbor up, or any source here, I'm not being picky. And I want to send a message to my next neighbor up to send. My send here is my next neighbor up. So, or next neighbor down, actually it looks like, oh no, next neighbor up. So I want to send a message to my next neighbor up. So this posts my send and receive. It says, try to receive a message and try to send this data, but take your time in doing it, or as much time as you need. I know you're not going to block me here, but I don't know when you're going to finally finish. So that means we could go off and do other stuff right here. When I talk about overlapping computation and communication, I say it's a nice thing to do to hide some of that communication expense. Well, indeed, this is where we could go and do anything we wanted to while we're waiting for the messages. But eventually we need the message because we've got to print the value out. And I don't want to try to print it before it comes in. So here's where I can do a wait all. I can say, okay, wait until the messages, are sent and received, and it'll wait. And then finally they're sent and received, and I can print the value out and continue on my way. So this is a way we could change our shifter routine and make it bulletproof. There could never be a deadlock, even though there's never going to be a deadlock with a single integer. If we made these messages 2 gigabytes in size, there's still never going to be a deadlock. It's always going to wait, do their sending and receiving in the background and then complete. And it would also potentially save us those extra copies of the data too, which for big messages that are gigabytes in size is expensive and wastes memory. So this is more efficient, and we never have to worry about deadlocks or anything. And you can see you can convert a blocking send and receive very easily to non-blocking. So this is going to introduce the idea that I hope sticks with you, that you don't have to be aggressive about optimizing MPI codes and using the latest best, most efficient method, which I'll show you some more of. Instead, you can start with blocking sends and receives because life is easy. Your code will hang for you nicely if you're not sending and receiving the right messages. Makes it easy to debug the code. And then when you've got a debugged code, if you're concerned that this could potentially deadlock with a huge message, or you're concerned about performance, you can change your sends and receives very easily into non-blocking versions without a whole lot of effort. And so here, for example, is one of the Summer Bootcamp Hybrid Challenge winners where they took and they overlapped the computation and communication because they did, they basically started the sending and receiving of messages here, the whole communication phase of their MPI code, while the second loop here was copying temperature to temperature last. So the communications all happened in the background, and they didn't wait until they needed the data for the next time step. So here is basically, it's a little bit of a spoiler, but not really, because most of you probably weren't heading in this direction anyway. Here's one way you could do the Laplace code. It's pretty fancy. Is they set up all their message passing in advance, and then they started doing, they did the first iteration of calculation here, and then before they continue on to do the copy of temperature to temperature last, they triggered all the message passing. So now all the message passing is happening while they look for the DT and while they copy temperature to temperature last, and they don't care about it completing. They can take as long as it wants, as long as before they go on the next time step here, next simulation step, the message is complete. So it's very easy to implement this stuff and get big computational wins and optimizations and whatnot. And you can mix and match blocking and non-blocking if you want. As you're adding this stuff to your code, you can send a non-blocking message and receive it with blocking or vice versa. And we're going to find out that there are basically, if you look through the index, non-blocking versions of most of the routines out there that are to do communication. They are these ones that have the I in front of them. So there's I send and I barrier and I receive and I gather and all of those. I barrier might sound ridiculous. You might say, why is there a non-blocking barrier? And non-blocking barrier is actually useful because here's a way you can put a barrier in your code and it won't actually stop the PEs, but you can check and see later on if they've all reached that point in the code without any of them waiting. So I can say, I could have a part of my code where I do want to block before I do certain things. But if the PEs aren't there, I might do other things. I have other stuff to work on. So I can work on other stuff and keep checking, oh, did all of my colleagues, did all of my other fellow PEs get there by checking this flag after the fact? So even non-blocking barrier, as ridiculous as it sounds, makes sense. Okay, let me see if we have some questions here. Nope, we're good on questions. Okay, then there's still more levels of optimization you can do. And in message passing communications, the next step up is single-sided or direct to memory or remote memory access type of communications. These are all kind of synonymous here. You'll see the mechanics of how they work. And the idea is that we don't want to, a lot of times, I mean, all we want to do is we've got an array here, A in memory, and we just want it to be over here on this other PE. We don't care how it gets there. We don't need to do sends and receives or anything. We just magically want it to appear there. And as a matter of fact, if we could do that, it would be even more efficient because things wouldn't have to go through send and receive queues and everything else. So can we do this kind of just single-sided, I just want to push this array into this memory, or from this PE's perspective, I just want to go and grab this data from this PE's memory. And indeed, MPI gives us a way to do this. As a matter of fact, it gives us some alternative ways to do this, or multiple ways to do this. And so this single-sided communication is a very popular next step to take to optimize MPI codes too. Or if you're experienced, you might just start writing your code this way. But at any rate, you can evolve your code painlessly to use single-sided communication. And again, it can be performance reasons because we're skipping a lot of buffer copies and everything else, or even algorithmically, it can make your life a lot simpler to have things just appear there. One example I want to touch upon a couple of times here as we go through this is that what if you've got an MPI code, and it's reading lots of data in from disk, it's parsing disk files, reading a bunch of data from disk and processing it. And once in a while, you get some bad data. And you'd like to keep track of all that bad data. You want a global counter somewhere for all the PEs to keep track of bad data. And so we can write a code right now with what we know that says, okay, let's have PE0 be in charge of keeping track of bad data. So PE0 just has to sit there and wait to receive a message from the other PE saying, this is add one more to the bad data counter. Add one more. Now we have 10 pieces of bad data. Oops, PE12 found some bad data. Increment this counter. But wouldn't it be nice if instead of PE0 having to sit there and pull all the time, look for that, wouldn't it be nice if PE0 just had a counter in memory and the other PEs could just go and increment that counter? They don't have to do a full handshaking message passing thing with PE0 sitting there waiting for messages. Can't they just stick it in PE0's counter. And indeed, with single-sided message passing, we can do that kind of stuff. We can go and have a PE just put into another PE's memory some values or some results. So from the algorithm perspective, it can be nice as well as the optimization perspective. So let's see how we do this here. Well, the most basic and popular way in MPI to do this, your basic single-sided message passing, is you define some data windows, which is MPI's version of saying you define some areas of memory that other PEs are allowed to access. They're allowed to either put data into or get data from. They can't just access PEs and can't just access all of the memory on some other PE. We're going to define some allowed regions where they can. And those regions are basically going to be some variable names. It could be an array in memory. So our A array would be a window, or a single variable could be a window. But a window is basically saying these are the variables that are allowed to be remote accessed. Then you want to remote access them. You can put data there, you can get data there. But one of the problems with single-sided message passing is, how do I know when somebody put data in my memory? Or, I don't know when it's finished moving there. And the answer is we need some flags to tell us that, or some fences. We'll see how to do that. So these are the three things we do for single-sided data. Here's our Pi code with single-sided message passing. And so we'll step through this and look at what's going on here. But basically, we had to define a window for the variables in our Pi code. So this is our Pi code that divided our circle up into slices, and then had each one of the PEs calculate a sum of that integration and then add them all together. So that meant that we needed to communicate with a couple of variables here. We needed the variable n, which is the number of slices that the user inputs for us. That comes from PE0. And we needed a total value for pi, which PE0 gets, right? In our original MPI code, this was something we broadcast, the value of n to the other PEs. And this was something we used a reduce for to get the final value of pi. That's all the other PEs need to know to operate on this code. So we need a couple of windows to capture, a way of saying, again, variables that are allowed to be accessed by the other PEs. So PE0 is going to create a couple of windows. These are collective operations, by the way, to create commands. They're collectives. What does that mean? It means all the PEs in the communicator need to participate. So these other PEs that aren't PE0, even though they're not going to have any windows on them, the other PEs don't need any windows at all. We're going to have PE0 is the only one that's got these publicly accessible windows, but because it's collective, they still participate. So again, in MPI, anytime you see something called a collective, reduce and broadcast that are obvious collectives, but in this case, the window create commands are collectives. That means all the PEs that share that communicator, in this case, the only communicator we've got is CommWorld, need to participate. So they call win_create too, even though they're not creating any windows. Only PE0 is creating some windows. So they all call win_create. Now we've got our windows set up. Now in our code, where we normally would do a broadcast from PE0 to the other PEs to let them know how many intervals the user wants the code to use for its approximation. Now instead, we let all the PEs that aren't PE0 get the value from PE0 straight out of its memory. They'll go and get the value for n straight out of PE0. So this way they go and get it. PE0 doesn't have to know what's up. It just has its value grabbed from memory. But again, how do we know when we're done with this operation since it's happening in the background? And the answer for this style of doing things is we fence off the regions, literally fence off with these window fence commands, the regions where we do our communication. And so whenever we're doing a communication, we fence the region off, and when we're done with our communications, we have another fence. And that means that the computation can run away knowing that the data is all valid here because it's been processed, and the communication can happen. And then the computation here knows that all the values that it needed, in particular n, right, because it needed to grab n to do this computation, n has been gotten. So when we do single-sided communication with this style, we still need to fence things off to separate our computation and communication phases. Likewise, we do our computation, and once more in the end down here, we need to do some, we need to reduce our values down. Well, the other synonym basically for reducing things when you want to add them together is accumulate. So we can accumulate our values. So MPI calls these accumulates, where it's basically doing a single-sided reduction operation. So this is where we used to have our MPI sum reduce. Here we have our MPI sum accumulate for single-sided communications. And this means that PE0 is going to have stuffed into its memory without it participating. All the other PEs are going to stick into PE0 this partial sum of pi. And how do we know when they're all done doing that so that PE0 can go ahead and print the result out? Well, we fence off again the communications. So I'll step through the routines here. We just covered the whole thing, but this is what we basically did. We created some windows, and we told it which variables are going to be accessible. And this PE0 happened to have the variables n and pi accessible. And you can do this also if you've got dynamically allocated memory in more complex situations. MPI works just fine with all those as well. Then we move the data using either puts or gets or accumulates for these reduction type operations. So this moved the data around. And there are versions of this that have flags, request flags, and everything else as well. And then we used fences to make sure that we separated our communications off so that we knew when the gets and puts were done. And so basically use fences to separate your computation and communication, and you'll be in good shape. That's the most basic way to it. There are some subtleties to it, and you could, if you're really comfortable and advanced with MPI, you can start to bend the rules a little bit. But I will suggest to start with, you basically just say fence off the computation and communication. You can give hints to this as well that might allow it to be smarter about what it's waiting for. But at any rate, for basic purposes, just fence off your computation communication. So again, here's the whole code. This is our fences to fence off our communication. And here's our communication, and here's our computation. So this is single-sided communication, which means it does no extra copies. Nothing's getting copied to any buffers anywhere in memory. It's straight from one memory straight to the other memory. So this is going to be more efficient and save us time. And depending on how you think, you might also think this is simpler then. I don't need to do anything fancier than just stuff it and stuff my results into memory. Okay, so questions here. Let's see. For the winner code, at which point winner is I'm guessing an autocorrect thing. It's not striking what you mean at the minute for the winner code. I don't think you got a typo in there because I don't know what winner is referring to. So let's see. Can fence be used for two-sided non-block communication like send and receive? No, it's not appropriate there at all. Does not apply there. Send and receive, you know the communication happened because something got sent, something got received. There's no meaning, there's no point in fence. We know it happened because we call the routines. So it's not applicable there. Just to clarify, MPI fence creates a barrier until the data window has been accessed. That's one, I mean, the more technical way, basically, yes, the more technical way is it guarantees that it won't continue past here until all the outstanding gets or puts have been completed. That's probably the more precise way to say it. Plus make code work without any buffer. Why MPI can't all be organized this way? With no buffer, the whole reason, we go back, and it's a good question, so it's worth backing up for. And it was yesterday's discussion when I first explained why MPI communication is set up this way. I said, there's a reason that all this stuff is happening in the background. And the reason, the number one reason is that after we send the data here with this normal MPI blocking sends and receives, after we send array A, we can go ahead right away and mess with A. We can have MPI send, and then we can have A12 equals 6 and know that that's always going to work right. We don't have to worry about whether we're messing with the data while it still hasn't been sent yet. The second we start doing non-blocking stuff and single-sided stuff, we now have this responsibility of keeping track of when things are sent and received before we can access them. So that's the reason blocking sends and receives exist, to make life easier to think about, less error prone. But you're welcome to do all of your MPI with the single-sided and not have the buffering. So when you say, why isn't all MPI with no buffering? It's because sometimes it's a lot less error prone and simpler to use blocking sends and receives. And if you're going sending single small variables around and whatnot, or if you're developing a code, I'll take that simplicity and that robustness. But yes, it has its buffering and its price to pay in terms of performance. But it's not just to be dumb, it's because this is organizationally much less error prone and easier to think of. As we get into the non-blocking stuff, we are starting to take more responsibility for making sure things complete on time and whatnot. But feel free to choose whichever one you're comfortable with. As you get more experience as an MPI programmer, you'll kind of jump to a higher level. I, for example, almost always just use non-blocking communications that I send and I receive just to develop that MPI code. It's just friendly and convenient in most algorithms. So I just write codes with I send that I receive right out of the gate because that's me. But if I had you doing the Laplace exercise or any of the earlier exercises without right out of the gate, it would be more confusion for you. You would have found things harder to get kind of working and understand what's going on. And so, there's a reason that all these capabilities there, you get to pick which ones to use. And we still got some more to explore too. No buffers, but it does network socket buffers internally, right? Well, it's internally means it's platform dependent, so there's no single right answer, but in the majority of cases, the network interfaces that we have available today, like the InfiniBand network cards that happen to be sitting in bridges, are smart enough to try to grab things directly out of memory and minimize any extra buffer copying they're doing. So they are not making any extra network buffer copies that they don't need to. That's why when we have things like user-defined data types, grab stuff scattered all over memory, they'll gather them together into a buffer once. They won't make an extra user space and then system space copy. So things are very well optimized with MPI. So behind the curtain, they're doing a minimal amount of buffering that they need to do. And by using these more advanced MPI routines, you allow it to do even less. What is the create and the else loop doing? Explaining what the create in the else loop. So I think you mean the window create here. So the window create here is because create is, and this is a good question for everybody, not just because of this particular thing. If you look at create, it's a collective. The second that something is a collective, you must have all of the PEs in that communicator, which the only communicator we have in our code, because it's simple, is CommWorld, have to call that collective participate. If we've got a broadcast collective, all the PEs need to call that broadcast or else the code will hang. So in our case, when create is a collective, all the PEs need to participate. An underlying reason is because they all need to know about how memory is set up and who can do what. But at any rate, just the simple fact that the command is called the collective tells you they all participate. Now, PE0 is the only one that's doing anything interesting and needs to define some real windows. So we want PE0 to call this with, with N and pi being defined as accessible windows for the other PEs. But because it's a collective, the other PEs have to participate. So even though they're not defining anything as their windows, they still need to participate. So they all PE0 is calling this at the same time the other PEs are down here calling this. So they're all defining these windows here, even though the other PEs are saying, you can't access anything on me, but this is also when they are finding out that they can access stuff on PE0. So the technical reason is they all need to find out what they can access where, or else these other PEs wouldn't know that they can access these on PE0. But the reason there's two separate branches here is because PE0 wants to define a few windows, the other PEs do not, but they all need to call create because it's a collective. Okay. I have a barrier after non-blocking send and receive. Does it ensure that all messages sent and received after the barrier? After a non-blocking send and receive, no. So if you have a non-blocking send and receive, so let's go back. It's another good question. Worth backing up to. Where's our shifter, our non-blocking shifter? So if we have in our code right here, set non-blocking send and receive. If I put a barrier in here, does this mean that all the messages are sent and received? Absolutely not. I can have a barrier in here and these messages could still be flying an en route. The only way to know that these messages are sent and received is to check their flags. So I could put a barrier here. The barrier will probably be passed if it's say the messages are huge or slow or whatever. I could put a barrier in here. They can all get to the barrier, continue moving on, and the messages could still be on their way. So barrier after a non-blocking send and receive doesn't mean the messages are sent and received. Only until we test or wait on them do we know that. Okay. Okay. Any point of using non-blocking, one could do single-sided with fencing. Yeah, non-blocking is a simpler iteration to go from normal sends and receives. It's very easy to turn them into non-blocking sends and receives. It's a little bit more of a commitment to go to this. So that's one reason right there. Maybe it's the main reason. It's easy to turn your send, but you can also do it piecemeal. There's you don't have to commit to one item. MPI is happy to mix and match these. So a very sane and reasonable thing to do might be for like this n value right here, which is asking the user for how many iterations. It's silly not, you could just do that with a regular broadcast, send and receive. Who cares how optimal that is? It happens once in your code and it's sending a couple of bytes. It's silly to actually do all this overhead of doing this fencing and everything else to send pi. And actually even the reduce operation is pretty much it. This is actually in some sense kind of silly. Why wouldn't I just go with the original blocking sends and receive version here? That's going to work just fine and be pretty optimal. We're not sending around big chunks of data. So this code right here probably should just be blocking sends and receives. And you're not optimizing much at all. Even if you scale this up to run on 1,000 nodes and very high precision integral, the operations it's doing here are already pretty simple. A simple broadcast and a reduce. all the work's happening in the computation. So here's a code. If somebody did it like this, I'd actually be like, why are you complicating things? On the other hand, with the Laplace code, the data structures get really big. If it's, huge data structures in 3D and everything, and somebody says, I'm trying to optimize this code, I'd be like, well, why don't you just do single-sided communications? It's not that hard to do for the parts of your code that are doing all the serious ghost zone exchanges, the big chunks of data. So you can mix and match things, but it's silly to just go super optimal to send a single integer around. And also it's silly not to optimize your code with this if it's big data structures, and a lot of time is spent copying buffers around, because this isn't that hard to do. So using the right tool for the job is not hard with MPI, because you can mix and match, and you can evolve your code. You can optimize your code. And if I were optimizing the code, I would never just do the simple broadcast, use this overkill right here. Does the window go both ways, getting and putting? When you open the windows up, yes, with these windows allow both gets and puts. So you don't specify in the windows reading or writing for these windows. Okay, but this is not all there is to say on single-sided communication. We might already argue, you might object a little bit, that is this really single-sided, since we have to have these fences in here? I mean, really, we say PE0 is not participating, but we still have to fence things off. It does have, PE0 is aware of the fact that communications are happening. PE0 really can't be off in its own world doing its own thing with the way we've done this, right? It's got to participate in these fences. Is that really single-sided? Well, the answer is we could take it a step further. We can have really passive target remote memory access with MPI as well. We can set some windows up, and then participating PE doesn't have to know anything about it, even be in the region of code. And the way we do that is we set up some windows that we can lock and unlock, even on remote PEs. So the PE that's involved, say PE0, doesn't even know that other PEs are locking and unlocking the windows on it, and then doing puts and gets of variables there. So this is truly passive. As a matter of fact, but this now introduces things like the PE even accessing its own window. So if PE0 wants to see what the value is that's been accumulated there, it needs to lock the window just so other PEs aren't simultaneously accessing and messing around and causing issues. It locks its own window even to look at its own local variables, but it can do it at its own time when it wants to. So we no longer have to have these kind of coordinated fences, but you do need to lock and unlock windows to have exclusive access to them. Or kind of exclusive access. You can say, I'm only reading this window, so I don't really need to lock it as long as I don't really care about what the precise updated value is. So you can make things exclusive or unexclusive, but you need to window by window grab other PEs. So this is really the next level up of really being truly single-sided. And so you need to allocate these windows. They can be dynamic memory and everything else, but now this is really passive. And now we can do the dream of actually doing this counter I talked about, of having PE0 have a counter in memory where all the PEs go and update this counter that PE0 has, but PE0 can be off doing disk IO. It doesn't need to participate in fences or anything else. It's off doing its own IO thing, but it has a variable memory that the other PEs can update in memory. They lock the window, and then they accumulate, add one to say one more bad value there, and unlock the window. And so this is how we now have really passive access to those. Only thing is, you do now have to worry about something we worried about earlier with OpenMP, where you've got something in memory that can be multiply accessed remotely by other PEs. The way we saw this with OpenMP, so what I'm referring to is back in OpenMP, I said we had a variable called, it was our prime number example. We had a prime number solver, and we had a variable called primes, and we had different cores adding 1 to prime. We said primes equals primes plus 1. And I said, we have a problem here if this is a shared variable, because when a core goes to add 1 to prime, what it really does, it goes and grabs prime, brings it back, adds 1 to it, and then writes it to memory. And at the same time, other cores could be doing that. So we found one answer with OpenMP was to make private copies of prime and then reduce when we're done. And that was fine and logical. Here we have the same problem though. If we have a counter in memory on PE0, and we have multiple PEs that are going off to PE0 and adding it up. And remember, this is on a cluster. This could be on a very big cluster, and our PEs could be very far from each other. So the time to go and grab that variable and add 1 to it is a long time. I want to go off and grab my bad data counter and bring it back, find out it's equal to 12. I add 1 to it, and then I write it back to memory. Well, while that's happening, there's plenty of opportunity for other PEs to be trying to increment that too, and they're all trying to increment it, and then we end up with this undercount issue, the same as with the prime number counter. Well, MPI has the ability to do atomic operations. I said that's referring to something as being an atomic operation, which nothing can interfere with that operation happening. And by default, you can see lots of things can interfere with that operation. Well, we have an MPI, the ability to make things atomic if we want to. So if we want to go ahead and fetch something and then accumulate something to it, add something to it, for example, we can do that, and MPI will enforce it. It'll say, I'm going to go and get this and bring it back and lock that out. Nothing else is allowed to interfere in the meantime. So we can deal with that kind of issue as well. And there are all kinds of other synchronization things we can deal with, or maybe have to deal with, depending on your algorithm, as we get more single-sided and asynchronous. So again, the reason you start with blocking sends and receives is it's very clear what the state of the machine is at any point in time. You know whether a message is sent or whether it's received because it's blocking on that receive. It's not going anywhere till it's received. And as we get more and more asynchronous, and we have to take more and more responsibility for keeping track of all the balls that are in the air with messages, all the things that could be happening. And we've got this truly passive single-sided message passing going on, right? It is now even more our responsibility to make sure that everything is updated on the same time step. And P0, when it goes to look at a value, it's the final value, and there's still some outstanding reference to it. So we need to take more responsibility, but MPI will give us all the low-level tools we need to deal with that if we want to. So that's the reason why MPI doesn't just say, hey, do everything single-sided communication. It's harder to be absolutely correct with that. And it would be silly to do that for small messages and whatnot, where we don't need the performance. Why introduce the complication? There is one last actual, even more optimized version of RMA that MPI has, which none of you will probably find yourself using unless you become a very hardcore MPI programmer writing things like compilers, PGAS compilers and whatnot. And that is for very, very super exascalable codes. So if you're running on an exascale machine with hundreds of thousands or millions of cores, you might also like to make sure that your communications, even setting up windows and whatnot, is only your nearest neighbors. Because nearest neighbor communication, as we've seen for our application like Laplace, is all we care about. PEs only often need to care about their nearest neighbors. Not always, of course, but for a lot of applications, most of the communications, nearest neighbor. You're only communicating with halo zones or whatever with your nearest neighbors. And so it's nice to have a kind of windows that you can set up only with your nearest neighbors, completely independent from everybody else. And MPI allows you to even do that. So we can set up windows that are only with our nearest neighbors and communications only isolated to our nearest neighbors and nobody else. But again, you will only need this level if you're really working with exascalable codes. And again, you can incrementally evolve your way here too. So this is if you're already doing single-sided communication and now you decide that it's too expensive to define windows and whatnot when you've got a million cores. But anyway, the main takeaway I hope you have here is that optimizing message passing in MPI can be incremental. You can start out with the easiest thing for you to develop and you're most comfortable with. For most of you now, it's probably blocking message passing, I'll suggest. For more experienced MPI programmers, you might just start right here with everything. And then you can take for the parts of your code you care about, and you can start to say, I think this might work better here. Or it might even be natural to write from scratch with the single-sided communication for certain things. But anyway, it's up to you. And you can mix and match, and it's perfectly acceptable and viable and sensible to do exactly that. So a lot of MPI projects, yeah, you start with regular non-blocking message passing, and then you decide, here's a few, the real computationally intensive parts of it, and I'm going to go to single-sided message passing, and maybe passive makes it easiest to implement, and you can do that. So there's a lot of capabilities in MPI. Let's see. To understand correctly, this complicated stuff can improve performance fees, will not minimize communication time or memory management. No, it will absolutely minimize communication time. For example, single-sided stuff doesn't do any of the buffering at all that's going on, and that saves an awful lot. Doesn't have to do the same level of handshaking that things are going on. So no, it will optimize communication a lot and memory management as well. You don't have all these extra buffer copies flying around. That's a huge win for real size messages in scientific codes. So this saves an awful lot. I mean, basically the point is that we're going from, this model right here, which is kind of the default starting point, which again is fine for, an awful lot of small messages and debugging and starting out, to this. Boom. So we're saving an awful lot of all kinds of stuff going on when we do this. Okay, I lost my place. I think we were here. you name some exascale problems? Dwarfs. I don't know what dwarfs refers to right there, but exascale problems. I will talk about exascale problems in our outro talk extensively, and I'll give you even an appendix with a whole lot of great, relevant, important, high-profile exascale problems. And we'll see the relationship to MPI even. So outro talk, we'll have plenty of those, although you'll have to ask me what you mean by dwarfs, because I don't know what that means. Can you explain again the difference between lock and fence? They're two different. So basically, fence means all the PEs. Fence is a collective operation. All the PEs need to participate in it. So even though it's called single-sided, the PE that's being affected, like PE0 in our Pi code here, is still got to participate and kind of stay synchronized with what's going on. Whereas when we have these windows, these passive target windows, PE0 could be off doing completely separate code, have no idea what's going on, and we're still accessing its data space, its memory, writing variables there, getting stuff out of memory. So that's the big difference, is that this is kind of much more coordinated. It's single-sided, so it skips all the buffer copies and everything, but it's more coordinated. This is much less synchronous, much less coordinated in terms of just passively sticking things and getting things out of memory. Okay, so we're caught up on questions. Another thing that comes to mind when people worry about capabilities here is can we start and stop PEs in midstream? So far, we're starting everything with MPI run -N8, and then we got 8 PEs for the course of our run, and that's it. That's how many ranks you got. And that is going to be, for almost all of you, exactly the kind of environment you work in. You work on a supercomputer. We can't let your code in the middle of running grab 1,000 more PEs, because that just would be anarchy. And that turns out to be the reality on the vast majority of systems. So most of the time, that's exactly the constraints you're stuck with. You start your code running on a number of PEs, and that's it. However, you can think of problems where it might be nice to expand the number of PEs your code's running on in mid-run. It's got more work to do, or it's finished work. It could give some PEs back to the system. So MPI theoretically allows you to do that. You can actually dynamically start new tasks up, and they come in a new communicator, right? Because your world communicator is different now. You got a new world. So you can theoretically do this with dynamic process management. In reality, again, most systems just don't permit that to happen. So don't get too excited about possibilities of having your algorithm be flexible and grab more PEs as it's running. Not only is that kind of complicated, although the cases where you want to do it, like a lot of work farming and that, it wouldn't be complicated to do. It's just most environments won't support or allow you to do that. Another thing you shouldn't get too excited about its capability is MPI-IO. MPI has built into it some nifty IO stuff. And it is kind of nifty because it leverages the collective operations and the data types, user-defined data types, and it allows you to basically say, I've got a bunch of data distributed over these PEs. I can write some simple routines that go and collect all the data together and write it coherently to disk. And it sounds really good and nice. And it is on paper, and your code looks nice. The problem is, performance-wise, this usually isn't a big win. So this is one thing I caution people away from, which is using MPI-IO with high expectations. And the reason for this is that file systems are very, very platform dependent, configuration dependent. Parallel file systems, which is all I'm even going to talk about, because if you're writing seriously parallel code, you're going to be running on a seriously parallel file system to deal with the amount of IO you have. Real parallel file systems are meant so that your programs can do something like this: have a bunch of PEs, and they all want to write to a file. They want to write the output file. Our Laplace code, we want all our PEs to write the output file. Matter of fact, I gave you a sample piece of code you could stick in the Laplace code for visualization to do exactly that, right? To an output file. So this is what happens a whole lot. Problem is, real parallel file systems actually have some hardware between the PEs and the file. So all the PEs want to write to the file, but they end up going through some intermediate metadata servers or things on the Lustre file system, which we have on Bridges and is the most popular parallel file system. They're called OSTs. There are other parallel file systems, GPFS and whatnot, that have similar things. But the bottom line is, having thousands of PEs write to the same file, or even write to separate files, but having thousands of PEs writing simultaneously can quickly become a bottleneck. On the biggest machines these days, exascale machines, they have hundreds of these OSTs, or even a couple thousand, but still having all the PEs write at once is going to cause these things to saturate and be a bottleneck. MPI-IO doesn't know about this kind of stuff, and this will by default kind of be what happens. On the other hand, it is very, very easy to write some regular MPI code to do the more optimal thing, which is to only have a small subset of PEs do all the writing to disk. And that ideally that subset is close to the number of OSTs that you have available to you. Ideally, it's actually a little simple parameter in your code you can change as you move from one machine to the next, or one environment to the next, to kind of say this has a big wide parallel file system. But at any rate, what you want to do in your code is have all the PEs send their data to a smaller number of PEs, which write everything onto disk. This usually works very well with both the disk systems you find on modern machines, as well as the fact that the network bandwidth is very fast. So this is a lot faster to do than trying to send directly to the drives. Anyway, this combination turns out to be simple to implement. It's very easy to write this code. So if you've got an existing code, it probably has IO section anyway, dump results. And if you go into dump results in an MPI code, it's not hard. It's usually a couple dozen lines of code at most to let it do this in a nice flexible way. You got one variable in there called number of writers, and it says how many PEs are going to write, and then all the other PEs just send their data to write. And if you do this, you end up getting sometimes incredibly good, close to theoretical maximum performance, which can be hundreds of gigabytes per second on big machines these days, or actually you can cross the threshold to terabytes. But you can get hundreds of gigabytes per second if you do the right thing. If you do this thing instead and just have them all try to write to disk, it'll be terrible. And so MPI-O isn't good at recognizing this situation. So it's nice and it's elegant, but I encourage people to instead take the hour to write this version of it instead, and then you'll be pleased with your performance on whatever system you're on. You should be able to get near its maximum performance. So anyway, that's my caution about one feature to stay away from in MPI. Otherwise, use all the features that are out there. And MPI-O also does work here and there well, but it's just, it's the one thing where people sometimes are disappointed. Okay, let's see. A few more random things we've stuck on to the end. Let's see. OST stand for OST. Ooh, I knew this. I've used OST as the acronym for so long. Just type Lustre, L-U-S-T-R-E, that's how it's spelled. Lustre OST, Google it, and it'll tell you. I forget some. It's just a metadata server, but I forget what it stands for at the moment. Okay. Fortran 90 has these wonderful array operations just built in. Well, Fortran, I should say these days. If you're not using a newer version of Fortran 90, you got problems because that's 30 years ago at this point. So Fortran built into it has these wonderful array operations. And you might say, when I do an MPI send for a column like we're doing in our Laplace code, why can't I just use this array operation? Say send the whole column. Well, that's a good question. And indeed you can. The only problem is, or potential problem, is that in Fortran, when you do something like this, you use a subsection or a slice of an array. Fortran can carve out a little temporary copy of that, a little buffer with a temporary copy, which is kind of what you want here, and that's fine. The only problem is when you do something like isend, remember, is the non-blocking send says send this buffer, but you don't have to send it right away. That's the whole point of it, not blocking. Let me know when you finally send it by changing that request flag. Well, Fortran compilers, when they see this, they see isend use this temporary array, and then it returned. Fortran compiler by default will think it can get rid of this temporary copy immediately as soon as it returns from this call. Meanwhile, you can't. You need to leave this buffer hanging around for a while. So since you don't have to do it's nice you're not doing the manual memory management like you are, in C or something, but it's error prone because it can delete this buffer before it's actually sent. So you need to check if you want to do fancy stuff like this, which is perfectly fine to do and makes sense, and make sure that it's supported by your compiler that's smart. And the way you can do that is you can see if subarrays are supported with your compiler. So if you're not sure, stick with basic MPI data types. If your compiler is smart, then yes, you can use nice, beautiful Fortran 9, Fortran style array shapes and slices. And it is very pretty and elegant to use in your code. Likewise, C++ brings an awful lot of nice stuff to the table too, because a lot of these MPI routines have, redundant, silly parameters and everything you're always filling in, and shouldn't it be able to infer some of these itself? And indeed it can. As a matter of fact, if you look at the boost version of MPI, you can see you get really nice stuff like, hey, here's the world communicator, and we want to send something from this rank to this tag like this. It's really clean. It's much nicer. It looks very pretty. So C++ boost MPI is very pretty. But now, of course, you're like, Boost is probably familiar to many of you using C++. Question is always, do I use Boost or not? Well, I'm rolling in a huge library with all kinds of stuff. It's not official, but it's pretty popular, so it's pretty well supported, but not always. So question is whether you want to rely on Boost or not, and that's an open question. I leave it up to you. MPI actually had a straight up C++ interface all the way up through 2.2. The MPI committee is huge fans of C++. They do not dislike C++, but they did realize that C++ has so many performance-specific issues you need to be aware of. It was just impossible to make it work right in a normal generic way. They say STL, thing. So it's not a unique to MPI kind of thing. It's just C++ performance is a matter of all the things you can't do. And the MPI spec can't be full of things you're forbidden from doing as part of the language. So anyway, they finally gave up after a very, very valiant effort. And so as of 3.0, it's no longer an official first-class language. Now, it's not a big deal. Like I say, of course, you can use C routines from C++. That's no problem. And you could grab Boost if you want to use, really nifty object-oriented stuff. So it's not a problem. It's just hey, that's inevitable when you're dealing with C++ and optimization, and particularly with the evolution. C++ 11 didn't make it easier, and C++ 17 and 20 are certainly not making these any easier as well. So you've got to be aware of particulars if you want to use C++ features and still get things to work right. Likewise, Python. Python has a nifty project to give an MPI version, and it is MPI for Pi, and it is very, very friendly and easy to use. But like everything in Python, there are performance compromises, which can be somewhere between marginal or awful, depending on what you're doing. So if you grab MPI for Pi, one thing I'll encourage you to do if you want to get any performance whatsoever is do not use the default. And you can see how it's very clever, nice, clean syntax, right? Like here's a broadcast. Here is, we're broadcasting a number of intervals. And the root is 0. Wow, how clean is this, right? And this is very, very pretty stuff. It's a lot easier than all the parameters we've got floating around in our C interface to this, right? So it's very pretty, but the performance, again, has all these issues. With particular Python objects are, for anything performance object oriented, always an issue. So you want to use NumPy, which might not be a bad idea anyway, because you're already probably using NumPy if you're trying to get any performance at all out of Python. If you're using NumPy, then you want to use the special versions of these routines here, which have this capital letter. That's why I highlighted them in red right here. So make sure if you're trying to do anything in Python with MPI, make sure you use, if you're already using NumPy, make sure you're using these uppercase version of the routines, because then it's not using Python objects, it's using the NumPy array objects, which are behind the scenes, C. So make sure you're doing this if you want to use Python with MPI, but it's a very clever, clean interface. Almost every language that aspires to do anything distributed has an MPI binding. These ones I can vouch for, as in they're actually workable and well supported and everything. There are plenty more out there, but at least these ones you shouldn't be afraid of using if you use those languages. Let's see, here's some more random stuff. We're running out of time, so I'm gonna rush through it, just quickly introduce you to it. MPI has added on to everything a lot of, it's added attributes, basically a little key store database onto communicators and data types in Windows. So if you're writing your own algorithms, it's a pretty nifty way to just roll into the algorithms, the parameters and pieces of data information that they should have. It's more advanced thing. This is something though everybody should know right here. So it's the reason it gets a separate slide. And that is the fact that the timer in MPI, W time, is fantastic. Timing codes is always a pain in the butt because it's very important. You should time your code silly. It tells you your performance. It can alert people when you move to a new platform or a new compiler that something's broken. All of a sudden, hey, my IO time went from being 5% to being 50%. What's wrong here? And then you find out that somebody's got the disk system striped badly or something. So it's good to have timers all over your code, and it's easy to stick them in. And it's even easier if it's an MPI code, because the W time routine is straightforward to use and at least microsecond, usually better timer even. Whereas trying to find a nice timer, generic timer that's also got good resolution is always an open question. So anyway, this is a solution for that. If you're writing MPI codes, I suggest you use W time and stick it all over your code. Use it for performance insights. MPI 3.1, the latest version, is what we've been using. We can see it's already pretty mature. It's been around for 7, 8, 9 years now. Everything's implemented it fully and well. It added in some nifty features. It skipped the things it couldn't implement well. I think we talked about most of these features right here. What did they not do? This is why MPI is so successful. Is the committee is very smart about not rolling in features that can't be universally supported, even though they're really desirable and nifty. So, for example, interrupt-driven messages and receives. We're talking about, messages come in. Wouldn't it be nice if they could automatically trigger the code that receives them and do the right thing? A lot of algorithms, that'd be simple, and a lot of hardware is capable of doing that, but not all hardware, and it's not capable of being done in a portable way. And the MPI people have learned to avoid that. I think the MPI-IO thing way back when probably taught them that lesson, although they've always been good from the beginning of making sure everything is very portable. And that is why your MPI codes are incredibly portable and will perform very well on all kinds of networking configurations and everything, because the committee avoids doing clever and attractive things that can't be implemented well everywhere. That's hard for committees to do. Like the C++ committee we were just talking about, it's like the opposite. If the language evolves and adds features at an insane pace, to where that's the #1 criticism of people who use C++, of which I'm one. I'm a fan of C++, but the specifications absurd, and the rate it evolves is crazy, and it's a huge drawback for support issues and everything else. That's a trade-off. Now the pluses are we get all these great features, but MPI committee has stuck firmly to the other philosophy of everything we do will be implemented on all the distributions widely and well. And so they avoid these extra features. And when I say other implementations, it's something we've avoided talking about so far because it really is a non-issue. A few people have asked some questions alluding to it. MPI basically has a number of implementations out there. There's maybe 2 big families that open source families people draw from: MPitch and its derivatives, MVA-pitch, Intel version, et cetera, and then OpenMPI. They're both very popular and widely used. They are 100% compatible. There's no huge performance differences between either one. Some of them have marginal performance, better performance, on a reduced operation using an InfiniBand card. You'll see somebody say something like that. I like OpenMPI because my code uses a lot of barriers, and on this Mellanox device, MPitch performs a little better. Or, the Intel compiler comes with this version built in. So there are minor preferences that people have, but none of them are like, hey, my code only runs on this. Actually, I do see that occasionally. And it's usually a sign of a very broken code that has hidden errors people aren't aware of. If your code only works with one implementation, I will tell you more than 9 times out of 10, your code's broken. You just don't know it yet. You've been getting bogus results or something. So, but the implementations there are multiple ones, but they're all good and compatible and all get pretty good performance to perfect performance. That's the only dividing line between them. So anyway, that's all said about implementations. Some areas where MPI has things that can't fix are fault tolerance. So far, questions have come up. I've said MPI codes, you write them like the machine's 100% reliable, and nodes aren't going to break and disappear. And that's because fault tolerance is an extremely difficult problem to address. There's no good solutions for it. Every solution you come up with, which you think is clever and smart, is also very expensive in some other fashion. And so MPI recognizes it can't solve the problem. The best it can do is let you know in a better fashion when the nodes are down and break. And then if you want to write your own fault tolerant code, go ahead, but it's very difficult to do. Hybrid programming is a separate topic we are going to talk about. So I won't talk about that here. Let's see, we talked about Fortran 90 interface is nice. But with Fortran 2008 or onward, there's now a header file you can bring in yourself. It'll do better type checking. It'll use array subsections. We talked about that. iError, the error condition that's on the end of the things, is now optional. So actually, if you want to skip checking, the error parameter, you can skip that. And that's all there. You just have to use the 2008 header file or module. Do I have the name of the module here? No, you should use the 2008 module, and you'll get all these benefits automatically. Tool support. We're going to talk about tools, in particular debuggers and profilers in the tools talk, so I won't talk about that. So we're going to finish up here and say this whirlwind tour of all these features and everything. Which ones should you use? Because it can be overwhelming, and it's not going to be a problem. You can start out using whatever you're comfortable with and whatever you can debug well with. For many of you, that's going to be send and receive right now, or the very, very similar I send, I receive. And you can move from one to the other very easily. And then as you get your code working and you get more experience and you find where your code might benefit from some better optimization, you can add in some single-sided communication where you think it's effective. But don't worry about the extra scalability stuff and everything else until you're at some point where you're very experienced. It's an issue for you. So don't feel compelled to learn, look through all the MPI stuff, or you're going to start your project on the wrong foot and regret it later on. That won't be the case. Now here, for those of you that think you know MPI well, here's a little problem that we use to test people at our International High Performance Summer School. This is a program we run every summer. Sadly, virtually this year, but still international. We run every year. People coming in can say whether they know MPI or not, because we have different tracks. And the people that say they know MPI, we have a test for them. And it is funny that about half the people that claim they know MPI can't do this problem right here, or don't get the right answer, and they should. But this is slightly tricky, and it's a good test for those of you now that are starting to get comfortable with MPI. So here's the code. It basically says an even rank, I want to call this reduce. If I'm an odd rank, I'm calling this reduce here. So what is the answer you're going to end up when it prints out this even sum and this odd sum? And so we can come back to this at the very end of the day if you want, but then what's the answer here? And if you really are understanding the subtleties of MPI now and how it works, you should be able to come up with the right answer here. And I will give you the hint that you should hang on to, which is that collective operations need to be participated in by all the PEs in that communicator. Always remember that. All the PEs need to participate in a collective operation. So anyway, we'll stop with that because we have a ton to get to, and we're still okay on time. We're not desperate on time yet, but we can't lollygag too much. Okay, the next thing I want to do is I do want to keep this. Oh, some questions. In order to leverage the optimized I/O graph, we need to accumulate data to dedicated PEs. So basically, the special PEs, the writer PEs that you have, they just, the data gets sent to them as regular MPI messages, and then they just write it out to disk in the right order. So that's all they do. They don't really need to do any operations on it. That's why it's so easy to write that code. It's just send me your array, and I'll write it to disk. That's all there is to it. And then that ends up being much, much faster than all of them trying to write their array to disk independently. Okay. Wonder, Tom, did you know that off the top of your head? Object storage target, or did you Google it? I've long since forgotten.
I cheated.
Yeah, I figured. Who can remember those meaningless acronyms? And Tom deals with OSTs and file system issues every day. So, okay. So let's tie together a lot of the things we've done and also look at the things we haven't done. What are the things we haven't talked about? I keep assuring you that, OpenMP and OpenACC and MPI cover all the bases here. Well, is that true? Why are there all these other things out there? Well, let's take a look at it. First thing I want to do, though, is talk about how successful are you with your MPI or with your parallel programming in general? How can, if somebody tells you this is great or this is bad or my program is great, or you want to ask yourself how well you're doing parallelizing your code, how do you quantifiably, determine that? And for most cases, the answer is quite simple. How well does your code scale? If I've spent time parallelizing a code, can I run it 1,000 times faster or 100,000 times faster? That's what we're really after. And the answer to that is usually contained within a nice graph of scalability that anybody talking seriously about their code or their project or their language or their library should be glad to show you some scalability graphs for real problems. And this is what a scalability graph looks like. It says how much faster does my code run as I run on more processors. If I run on 1,000 processors, is it running 1,000 times faster? And if the answer is yes or close to it, great, congratulations, your code's scalable at that level at least. But most codes will have, all codes at some point will have something that tails off like this. They're not perfectly scalable. If I run on 1,000 nodes, I'm only running 600 times faster. And is that good, bad, or otherwise? Well, at least we can compare it to things. But first, when you scale your code up, there's two ways of doing it. So I want to be clear on that: strong scalability and weak scalability. Don't let the terms make you think one's more valid than the other. There's two different cases, but they're both valid. For our weather modeling code, for example, we might want to scale it up and run it on a machine for different reasons. Weak scaling is because we want to take the problem we're starting with, and we want to make a bigger, finer grained, higher resolution problem to get maybe more accurate results. So as we run on more processors, we run the same problem but we want to get more accurate results. So we run it on a finer and finer grid. We get, so actually it's a different problem in some sense. We have a different problem that scales up as we run on more PEs. And that's very valid and important to do. It's a lot of the times the reason you're writing a parallel code is so that you can attack bigger problems. And that's weak scaling. On the other hand, sometimes you're running parallel with the same problem on more nodes so that you can get a result faster. And that's strong scaling. And a very compelling reason to do that might be, for example, tornado modeling, something we do here on bridges during tornado season, where, tornado model can be super accurate, but if it takes you 12 hours to say a tornado is going to happen in 10 minutes, that's not very useful, is it? So for tornado modeling, you want to parallelize something so it can run faster, so that your simulation can tell you in 60 seconds that a tornado is going to happen in 10 minutes, and you can get the alarm out. So they're both valid cases, and they both apply across many different things in science. Sometimes, molecular dynamics, you want to run on a bigger, more complicated molecule. That's weak scaling. Sometimes your molecule that you're running right now would take you 2 years to run on your laptop. So you want to parallelize it so you can run it in 2 days. And that's strong scaling. So they're both valid. But when somebody talks about scaling, they should at least be clear which one they are. Now, one of the enemy of scaling you'll most likely hear referred to is Amdahl's law. As a matter of fact, when I first got involved in parallel computing, people used to say, I'm not even going to waste my time in parallel computing because of Amdahl's law. And it used to be a big argument that I'd have with them. Nowadays, it's silly. Everybody knows that all the leading edge research is parallel computing. It scales up largely. And so Amdahl's law is obviously not the threat that it might be perceived to be. But what is Amdahl's law? Amdahl's law is basically some simple math that basically says, if you scale and parallelize your code up, the serial parts are going to come to dominate the performance. Now, how does that work? It's very simple. We've got 100-second code that runs for 100 seconds here. So our code takes 100 seconds. And we go into our code and we take one of the subroutines where 50 seconds is spent. And we parallelize just that subroutine. And we parallelize it well. We throw some OpenMP directives in there and it really speeds up a whole lot. Okay, well now, when we take and run that code on a machine with 5 processors, that routine that we parallelized and sped up, it's going to speed up 5 times because we did a good job, and the code's going to run almost twice as fast. And on your laptop, hey, that might be victory. That was what you were after. But let's say now we take that code and we run it on bridges on 1,000 processors. Well, now on 1,000 processors, your code, this part sped up really a ton, and it's running in a fraction of a second, but the serial parts of your code are still taking 50 seconds. So on 1,000 processors, you're running improved by a factor of 2. That's not very impressive. We would not be happy with you using 1,000 processors on bridges to get that kind of performance. You would probably not be happy with your performance either. That's Amdahl's law. It's saying that if you don't parallelize the whole code, you're going to run into this bottleneck at some point. And if you draw out some graphs of Amdahl's law, they look like this. They say that if half of our code is not parallel, there's really no point in running on more than about 8 processors or so. It's just not going to scale up. But even if 1% of our code isn't parallel, we can see we're still going to plateau up here at a couple thousand processors. So really, there's no point in running on more than a couple thousand processors. And people that used to be afraid of Amdahl's law be like, everything's got some serial part of it. There's no code. It's not a couple % parallel. And most algorithms are a lot serial, blah, blah, blah. And again, it used to be a lot of arm twisting with people to convince them to invest in doing parallel coding. Now, of course, you can look on big machines out there and see people running on hundreds of thousands or millions of processors. And you open up any scientific journal and people are running, everything from molecular dynamics to climate simulation. Everything's being run in parallel these days, of course, as it must be. And so Amdahl's law apparently isn't quite the threat that people used to imagine. And how is that? It's because, hey, it is possible to write codes that have no appreciable serial part to them. It's not that impossible to do. Again, it used to be a debate. Now it's not a debate. The evidence is, the data is out there. It's not a debate. It's possible to write lots and lots of codes, lots of different algorithms, lots of different areas of science that scale up to tens of thousands of cores. So clearly you can write codes that don't have a lot of parallelism to them. But that will show up a whole lot in discussions about parallel coding with somebody that just doesn't want to make the effort. So you need to write some parallel code. What are your choices? Well, we could pick a language, or we could pick a library. We could pick a paradigm, whatever that is. We'll talk about paradigms, message passing versus work sharing or whatever. You got lots of choices. And if you look out there at different parallel programming environments, these are some languages and libraries and different approaches to parallel programming. There's an enormous number. I haven't updated this slide in years because there's no point, because there's every year dozens come, and every year dozens gradually and slowly slide into oblivion. There's no problem finding somebody with the latest, greatest, superior approach to parallel programming. Everybody's doing something because, hey, MPI programming is tough. OpenMP programming and OpenACC programming, people think even that's tough, although I hope by now you go, oh, wow, that could be quite easy, you know, at times. But it's not what people want. They want that parallel flag on the compiler that actually does everything in parallel. And since they can't have that, they want some magic language that does everything in parallel. So there's a big market for alternatives to the things you've learned this week, and it's huge. Problem is, you grab one of these here and you look at a lot of them, and a year or 2 or 5 years later, they, for all purposes, don't exist anymore. They're an abandoned GitHub project. And that's not so great if you've built your project around something and all of a sudden it's really not supported and is no longer functioning correctly. So you should be wary of just grabbing something somebody's enthusiastic about unless they can demonstrate that it's got some momentum and some committed support and some scalability. They can show you some scalability graphs on real applications, not some toy problems. Okay, so you have a lot of choices. Okay, what about if we talk about this from the paradigms perspective instead, the kind of general approach things are taking? Like for message passing, we used MPI. It's where we send chunks of data back and forth. Those are messages. For working with threads, we used OpenMP. That's where we're worried about threads of programming running on cores. And so we'll step through this list right here, but this is the way of kind of grouping things by their general approach to things. So let's talk about message passing briefly here. Okay, the pros we've been through. We said it's around. MPI is not going anywhere. There's tons of stuff for it to make it work, to help you out, whether it's books and algorithms or big libraries. You got tons of support for it and everything. And most importantly, just the evidence, again, you don't have to take my opinion for it. You can look at what's running on the big machines and what people are publishing results for when they say, you know, I ran this on 10,000 or 100,000 nodes. They're using MPI. So that's the result. That's the pro. Now you're in a position to discuss the cons, though, because you've seen it's lower level. We need to worry about details. In particular, we need to do this domain decomposition thing. And that takes some effort. And it can be, especially when somebody hands you somebody else's code, and it's big and stuff spread out all over, that's not fun. It takes a lot of effort to do. So MPI does take effort. So it's you know, start from scratch approach, as in, hey, we got to really pull the code apart and look at it from scratch. Maybe start from scratch is a little pessimistic, but it's a lot harder than throwing a few directives in our code like we could do with OpenMP, right? So MPI is great in many ways, but it's got some drawbacks. Well, how about data parallel? Data parallel, what is that? Well, data parallel, for those of you that are Fortran programmers, you already know, because Fortran 90 is basically data parallel. And for those of you that aren't familiar with data parallel, it's basically just having some commands that work with arrays in a nice, concise, simple way. Like, for example, if we've got an array A, we can just set it, we can say A equals 2, boom, the whole array is equal to 2. B equals, you know, whatever. Here's a for all for B. It gets equal to this. We can work with arrays in a nice array notation, and we can do things as simple as C equals A plus B, and we'll add 2 arrays together. Okay, you might think that's nice just because it's a nice notation, and that's why Fortran has it, because it's got a nice array notation. But it also buys us some magical parallelization in a very easy way, because all the compiler needs to do this in parallel is say core 0, take 2 and 5 and come up with 7. Core 1, take 4 and 2 and come up with 6. We can run this on 16 cores, and each core is only responsible for one math operation instead of having to do the whole array. You know, of course, that would be trivial. Let's pretend this is a much bigger array. The chunks are much bigger, but nevertheless, the point being, it's trivial to parallelize these kinds of operations. Very easy to do. Matter of fact, with OpenMP, we saw if you have operations like this, you can just say do the where all command in there, and boom, it'll parallelize the stuff. But data parallel languages like Fortran 90 are trivial to parallelize. Here's the communication. Here's how you move data in parallel. You know, is you just say, hey, do a shift on an array. Take the B array and shift it. And when you do a shift, it just shifts it, and boom, you got your new array. And behind the scenes, if these are multiple nodes, it can send stuff over the network and shift stuff around. It's very easy to figure out these patterns. As a matter of fact, these kind of data parallel compilers generate MPI code typically behind the scenes. They write the MPI code to do this stuff for you because it's very easy to do. So this is awesome. So why didn't we do everything in data parallel? It's so simple. You just learned some of it, or you already knew it and didn't know it. Very easy to debug line by line. It's great. So why didn't we do everything in data parallel? As a matter of fact, if we did the Laplace code in data parallel, it would be so simple, you wouldn't believe it. It'd be even simpler than the serial code. It's easy to write the Laplace code in data parallel. It looks simpler than the serial code. So why didn't we? Well, this is the real, why isn't everything in data parallel? And this is the real reason. It's because things that are just straight arrays are great and work great with data parallel. For example, if you're doing image processing and you get a bunch of pixels you're shuffling, you'd be crazy not to use a data parallel approach. It's just so natural. But the real world, our Laplace code turns into those turbine blades I'm talking about. It turns into exhaust mufflers and heat exchangers. Our earthquake codes aren't a cube of this. And the second that things aren't these regular arrays, data parallel has some problems. It gets very awkward very fast. And so you try to patch things together and make things work. But the real world is not regular meshes, and data parallel fails miserably in those cases. And MPI has all the tools to deal with all that crazy bookkeeping and whatnot to decompose things. So that's the reason data parallel hasn't taken over the world. Let's see. Tom's answered some questions about when the accounts will be around. That's it. Is data parallel available for C as well? There are versions that try to do this. We're going to talk about that of UPC and whatnot, but basically no, not straight up. Instead, C is taking a leap ahead with UPC. We'll talk about that in a second. PGAS languages, kind of a superset of data parallel. But basically, the only language that really builds in data parallel straight up well is Fortran. Well, now Julia has the same array type of syntax as well. They built it into the language. Say other languages, C arrays are freaking awful, and C++ didn't do any better with it. Python doesn't even have arrays in the language, so you bolt on something like NumPy. Java doesn't have, nothing has arrays except for like Fortran. Again, that's the reason it's still around. If data parallel was so incredibly widely successful, other language, there'd be other data parallel language. There are other data parallel would have just taken over. It would have put in the new languages. People would build languages around it from the get-go. But again, it's limited in that once you get outside of these regular array operations, it doesn't work. Okay, let's talk about the threading paradigm. And I say threads are a paradigm because it's a whole class of things where you're sharing work, or sometimes you could call it work sharing as the paradigm. The idea being that instead of breaking up our data like we did with MPI, how did we break up our work with OpenMP or OpenACC? We broke up our loops. We broke up the work. We didn't break up the data, we broke up the work. And so threading and work sharing approaches are great when they work. We know how to do this stuff now, right? We know how to do threads in OpenACC as well. CUDA threads are ugly as can be, but they're still threads. So threading is good and works. Only problem is it's stuck on one node. That's basically it. So I should kind of highlight in here wherever I get to that it is stuck on one node. The incremental approach is also awesome, but the incremental approach is where Amdahl's law will come to bite us. So incremental is great. We could do one loop at a time, right? That was wonderful. But one loop at a time also means the obvious converse of that is we're leaving serial pieces behind. So Amdahl's law is going to come into play the second we're doing things incrementally. But usually Amdahl's law doesn't kill us on our OpenMP nodes because we couldn't do bigger than a single node anyway. Amdahl's law can't catch up to you when you can only do 32 cores. Well, it could, but it's less likely to. It really bites you when you start doing hundreds of cores and whatnot. So the fact that threading approaches are limited to one node is a serious limitation. That's the ceiling. But well, it works great, right? Here are some alternatives because there are other things for threading that we didn't talk about. OpenCL I've mentioned in passing a few times. And OpenCL was an attempt to have an alternative to CUDA because CUDA is proprietary. CUDA only works on NVIDIA devices. And so that's distasteful and unsettling to an awful lot of people if you're to commit to something that's proprietary. And so an alternative to CUDA needed to be found, and a bunch of people banded together, including to their credit NVIDIA, and came up with the Kronos group came up with OpenCL, and it's alternative to CUDA. And so that was nice for a while in that we had an alternative that was open standard. It, like CUDA, is low level, so that's kind of ugly. On the other hand, well, it also had a drawback. It was never quite as performant on NVIDIA devices as CUDA. No surprise, right? What's NVIDIA really focused on? CUDA. So the open kind of standard is always going to lag a little bit. But that wasn't fatal. And so people were working with OpenCL because they didn't want to use CUDA for a while. But what has happened since is that, well, people that had the option moved to OpenACC to work at a higher level. And people even that didn't have the option found out that some of the supporters kind of abandoned it. Intel decided OpenMP was their focus for reasons we talked an awful lot about right at the end of Tuesday, or Wednesday, I guess. We talked about GPUs and OpenMP4, and we talked about how Intel has really gone full bore into OpenMP. So they're not so interested in this. AMD, they loved it at first because they needed an alternative to CUDA, but they went with HIP, and now they've gone other ways as well. So they kind of abandoned it. And that is bad news, because then if your industry players aren't supporting something that's very low level, the engineers are critical. If the engineers aren't supporting it, you're in trouble. And so when AMD and Intel and everybody didn't continue to support this at a low level, it's just the kind of thing the open source community can do casually. Amateurs can't really do device drivers and whatnot. So OpenCL is kind of really the performance gap grew bigger. And so it's kind of was not a smart thing to start any projects in. You'll still see code floating around, but you'd be crazy to start it. And the Kronos group even now has a successor to it called SYCL, which is absorbed. We'll talk about this down below. But they kind of, you know, so you don't want to start OpenCL, but you'll see it floating around as an alternative to CUDA. Fortran 2008, they brought out a threading library themselves. It is sophisticated, but it's not consistently implemented in all the compilers and everywhere. So I wouldn't suggest using it over, you know, OpenMP. Why would I deal with that issue? C++11 has very basic threads, came out in the standard. They've since implemented, did I have a note here somewhere? They've since implemented in 17 and 20 more basic stuff to implement to improve threading and futures and whatnot. So it's gotten better. So C++ has now better threading certainly than POSIX, the old POSIX threads, but also not nearly as smart as OpenMP stuff like tasks and whatnot. So I don't know why it's not compelling to use, but it's there. Python threads, Python has threading. However, the threads don't actually spin off real threads. And this is because of global interpreter lock, which now you're kind of in a position to understand. I think I mentioned before briefly, is that if you got a bunch of data structures and a bunch of things are operating those data structures, you want to lock all those data structures individually so that threads can one at a time, you know, mess with the data structure while other threads messing with it at the same time. Well, when Python was developed, they didn't perceive the need that anybody would try to use it for high performance. And so they said, like any other interpreter, why not just have one lock on everything? And that's what they have. And so with one lock, you can't spin off multiple threads. So there's a threading library that you can use. And it looks like you're creating threads, but they can never run concurrently. So it can be sometimes nice to do asynchronous stuff if you're doing like web server or something, to have a thread that it can time switch to. So it'll task switch to that thread. So it can run the thread serially and swap between threads, but they can never run concurrently. So that's why threading in Python will never get you better performance improvement. Instead, you have to resort to multiprocessing, which is multi-processes that don't share memory, and they communicate like our MPI codes then do with, you know, without the shared memory. So Microsoft has a threading thing, direct compute, but it's not HPC oriented at all. So I'll assume this audience doesn't care. Intel always has a bunch of threading things. They're promoting multiple ones. So they had threaded building blocks for a while. They had Silk for the same while. They still go to these web pages. They'll tell you, you should use threaded, TBB for all of your threads. Go to a different web page at Intel. You should use Silk for all of your threads. It's just madness. And they compounded the madness by now coming up with this one API thing. So which now at the moment they're promoting, this is the way you should do your threading. And it includes DPC++, which is an extension of SYCL, which is an extension of OpenCL. And it's just crazy, but it's the way that they say you should write codes that you might want to run on GPUs, and you might want to run on multiple cores, because it will spit out the back end. It'll spit out OpenMP if it needs to, or CUDA, or OpenACC, or whatever. And so maybe you buy into that. This isn't, but like I said, Intel has a long history of trying to do this. And the national labs started to support this heavily. And I thought, well, maybe, okay, at least they're all getting behind it. But then the other national labs support COCOS, which does the same thing. It's a higher level threading thing, which spits out behind it, OpenACC or OpenMP or whatever. And so even the national labs can't agree on a super framework that sits on top of all these. So investigate them, take a look. But I would caution against getting too vested in something that probably not all of these are going to survive, if any of them. Whereas OpenMP or OpenACC, you know, they're not going anywhere, but especially because these things spit them out. But anyway, that's the situation with threading. So it's very confusing if you start from scratch and do research, but I at least hope I've given you some insights into the pros and cons of those. Now, an alternative, because data parallel is so incredibly attractive to people because it's so friendly, and so the idea is so attractive that people aren't willing to give up on it. And instead, people have tried to make it more flexible with these partition global address space languages, which are basically trying to extend data parallel type constructs, these nice array things, but make them acknowledge a little bit that you actually are running on different PEs and you want some flexibility. And so they've been around for a long time. Co-array Fortran was around a long time. It's so long that it's now actually, it was in Fortran 2008, it was made part of the official language. So officially just generic Fortran now has these co-arrays in it, although they're not consistently supported everywhere. Even though Fortran 2008 tells you it's been out for a long time, right? And there's still a lot of most compilers still don't support it properly. But the idea is very attractive, but it just has never gained traction because by the time you get done making all these tweaks here to actually deal with load balancing and complex partitioning, you've basically done everything you do in an MPI code. So at the end of the day, most of the codes that they envision moving over to these PDAS languages have remained MPI codes. But there are alternatives for them. So as I said, Fortran absorbed co-array Fortran, and C has a version called Unified Parallel C, which is the same thing. So they're out there. They do have some traction and some support, and they've been around a long time. They probably will persist. They're probably both going to be around a long time. Well, this is part of Fortran now. UPC is not going anywhere either, but they just haven't gained a ton of traction either. You might notice as we've been doing our coding here, I keep talking about these general approaches in MPI. I keep saying this is the way, these kind of halo approaches are used in lots of codes. These are used in codes. You might say, well, why am I rewriting something if people have already using this kind of algorithm everywhere? And that's a good question. So people have gone and said, hey, there are certain patterns that we write with MPI that are so generically useful that basically you're just filling in the science. Even with our Laplace code, right? The science part of our code that does the Jacobi iteration, we haven't touched it. It's still there. It's kind of just dropped in the middle of the communication stuff you're working on. So why doesn't somebody just write the communication code generically for you and you stick in the science? That's not a bad idea. And as a matter of fact, attempts have been made to do this, successful attempts. Charm++ is probably the most popular one. Charm++ framework does a lot of really clever stuff. It's written in a nice C++ MPI. Got all the clever things I've mentioned in passing, like load balancing, dynamic load balancing and stuff. It does a lot of nifty stuff. And indeed, a very popular and important molecular dynamics package, NAMD, is written in Charm++, and it scales and works well. So you can use frameworks. They just are not as popular as I think they should be. For whatever reasons, they don't catch on as much. This is by far the highest profile application using a framework, unless you include, so here's something that just occurred to me as I'm teaching all this deep learning and AI stuff, and I'm using what essentially is a parallel framework, but nobody calls them that. The TensorFlow and PyTorch and other frameworks, they are that. So in the scientific world, if you ask people about using frameworks for parallel computing, they'll say, well, Charm++ is there, and you might want to look at it and use it, and they can't really think of a lot of other successes. But I will contend that a good example of that is all the stuff that people are doing now with these deep learning frameworks like TensorFlow and whatnot, because they're exactly that. There are tons of parallel computing that are done for you, and you just kind of drop in the connections that you want to make for your network, for your neural nets. So they're very limited in that they're really targeted towards doing neural net computations. So you don't want to try to co-op one of these for your scientific coding, but they are a framework that does parallel computing on lots of different devices that use multiple nodes and multiple GPUs and everything automatically for you if you just drop in your neural net definition. So it is kind of a successful framework. Hybrid coding, we're going to talk about this in a separate talk, so I will leave it for there. We talk about that a ton. So to sum it up here, I mean, parallel programming in a nutshell is you got to break your work up into something. If you break it up into a bunch of data pieces, break it up into individual states, that's where MPI comes in. If you break it up into just having your loops broken up into different iterations, that's where threadings or tasks come in when you use OpenMP or OpenACC or whatever, but you got to break things up. One thing we haven't focused on enough, because it will become important for many of you with problems, is the load balancing aspect. I've talked about it and mentioned it, so it's not entirely new. But with our weather code, for example, I implied we might break our weather map up into 50 states. If we did that, it would be it wouldn't perform well, because we'd find the PE responsible for Texas would be spending a lot more time with every minute of weather simulation than the New Jersey state PE. And as a consequence, most of the P's are going to be sitting around waiting for Texas or Alaska to get finished. And so this is not a good load balance. And so load balancing does take some attention. And as I said, it can get very sophisticated. And, in the case of our earthquake modeling here, we can see we end up ultimately with a bunch of PEs with some pretty weird shapes and some pretty weird communication boundaries between them. But that's not, you don't need to be a pioneer there. You can adopt the techniques that people use. And again, there are even frameworks, well, libraries are not full frameworks, libraries that help to do this work for you. Okay, let's see. We've talked a lot about scalability, though. These are all things we've talked about as we've gone through the code here. I don't need to talk about that. But to summarize things here, I mean, all of this parallel stuff we've done this week is driven by the laws of physics, making hardware look like it is. You're not going to get past parallel computing these days. Serial codes aren't going to run magically faster. Moore's law isn't even helping us out anymore. It's not a savior. It's parallel programming. It's going to be parallel programming. And the reality is, if you look around, you can take my word for it that it's, MPI at large scale and, an OpenMP and OpenACC are the most, the best way to go at, at the task level. But you should do some investigation yourself. A couple Googles around, look at some research papers in areas that are relevant to what you do. See how those people do their simulation and computing. And it's usually not but a few hops away, a few minutes away on the internet to find out that, hey, yes, indeed, this is how people are doing this kind of computing. And you can see, whether it's, whether you're, like I said, being a pioneer or an experimenter, which can be very dangerous, or whether at least you're following in the footsteps of people that have accomplished a lot of successful work. You can now make some pretty good assessments of what you know from this week. So once again, and maybe for the last time today, I think the last time in this workshop, you now have this piece with OpenMP. You can use multiple cores on any modern machine. Every modern machine has multiple cores. You now also have the extended skill of being able to use GPUs. And now with MPI, you can use clusters built out of those pieces as large as you want. How does this fit together for the future of computing? If we want to stare down the road a little bit, well, if you look on these roadmaps for the exascale machines and machines even beyond them that are being built, you'll see this term called MPI-plus-X. And it's a standard term you'll see. And what that means is everybody recognizes that the future of computing, scalable computing, is MPI gluing together some other alternative method to deal with the heterogeneous or the local hardware, the GPUs or alternatives to GPUs on the machine. So you'll see MPI-plus-X. By MPI, they mean MPI 3.0, the new version, because that's the X-scale version. New, I'd say, it's like 2012. But the X version is usually referring to something like an OpenMP or an OpenACC or a CUDA or some other piece you use with MPI to use the local resources, the GPU or whatever. But the term MPI-plus-X you'll see everywhere. Well, guess what? You are MPI-plus-X programmers. Now, again, you'll see people saying, well, but PGAS languages and their alternatives are gaining some traction. And I don't know that if they are, it's imperceptible. It's very slow. PGAS and their alternatives have been around a long time now. They've all been very well established, and they've got their niche. But they've been proclaimed as the things that are going to replace MPI, the unfriendliness of MPI for a long time. And the APGAS languages, synchronous PGAS languages, have now become quite long in the tooth themselves. X10, Chappelle, other ones are also, all coming up on decades old right now, and they've yet to displace MPI. So, but they are used, and they do exist. And if you were to say you're writing a code using, UPC, I wouldn't say, well, hey, in 5 years you're going to regret because your code's not going to run anymore. Whereas that might be true for an awful lot of other, like, should I write my code using Cocoa? So I don't know. 5 years from now, is Cocoa going to exist as a supported thing? I don't know. UPC will, and again, frameworks are things that are out there, but they haven't gained the traction to make them really significant. And there's always some computer science professor that doesn't do any parallel programming or any application programming that will tell you, well, if you just use some functional programming language like Haskell or something, it's so intrinsically parallel that it will automatically scale. And the answer to that is always, oh, that's fantastic news. Show me an application that's scaling. Show me the scalability graph for one of these applications. And that's where the conversation will usually take a very different turn, because the computer sciencey approaches have great promise always, but they don't materialize in anything. And again, if that sounds like editorializing on my part, I encourage you to look at the evidence. The functional languages have been around for 50 years, and that's not the answer to writing scalable codes. It's just writing a functional language that will automatically scale. That doesn't work that way. So this is kind of my projection of the significance of these things as we move into the future roadmaps. And it's not just me. Again, you'll see this in roadmaps. You'll see people explicitly saying MPI-plus-X is the foundation. We're going to deliver the machine day one with these components working. Past there, we hope these other things come up. As a matter of fact, you can see one of those roadmaps here with this exascale computing project. I'll quickly whip through some of these projects, and there's plenty more out there so you can see the kind of things that are going on. And these are the things that are going to be on the machine on day one, the applications that they're running. So this isn't just some grand design. These are the applications they've already ported to run on the hardware coming up on these exascale machines. And they're all different areas of science, all different kinds of applications. If you look at the pieces, so this is an appendix, so I don't feel obligated to explain every slide to you. It's here for you to peruse at your own time. The pieces that are in here are all things that work with and are built on MPI. So things like PETC libraries, MPI trilinose, and these are all MPI-ish kind of things if you dig into them, because they recognize that's how the machine's going to run. Here's the software stack, and these are all pieces of things that work with MPI. Like we're about to talk about these tools, Tau and PAPI. These are profilers that work with MPI at scale. The compilers all support this stuff. So these different pieces here are things that work with or they're built on MPI, most of them. I mean, there's some exceptions in here. But point is, if you're an MPI+X programmer, the machine that's being deployed right now, its roadmap is designed to support you from day one. And there are a bunch of apps. These are all things that run with MPI, from fluid flow and climate dynamics and whatnot. And so these are a bunch of interesting applications. I just pulled out a few of them I thought were a little bit different from each other. That's some diversity of the way they're approached. But you've got adaptive mesh refinement. So this is an example. The mesh changes as the code runs to deal with where the physical intensity is, where the computational intensity should be. And that's the kind of thing MPI can deal with. Other parallel programming approaches, this is where they get overwhelmed. So a lot of stuff here, and like I said, I'm not going to explain it, including machine learning stuff at scale and all over the place, and all different applications and domains. So I just wanted to give you a teaser, and there's lots more stuff out there, and you should certainly look in domains that interest you and are relevant to the kind of work you're trying to accomplish, and see what people are successfully using. Not what somebody's promoting, but what somebody's actually generating publishable results with. Okay, so with that, we will move into, I don't know which comes next, hybrid programming or tools, but doesn't matter because we're gonna whip through them both here. We're kind of okay on time, but I don't want to drag my feet too much. The tools, I've mentioned to you that we didn't drag tools into what we're doing here because it would have been a distraction. It wasn't necessary for what we're doing, but they're incredibly helpful, and you'd be silly not to use them as you get more serious about what you're doing and your applications grow. The two big classes of tools you should absolutely be using are debuggers and profilers. Debuggers, there's good news and there's bad news. The good news is there are a couple of fantastic parallel debuggers. They're very powerful, they're very capable, and they really do make life easy. The bad news is they are both proprietary licensed products. The licenses are not cheap, they cost money, and there's no open source alternatives. There are no open source parallel debuggers that are remotely worth using, that are anywhere near this capability. That is awful. Everything else we've done in this workshop is open source software. Matter of fact, I didn't even do this talk for a while because I don't like to talk about things that are proprietary, but eventually I recognized reality is what it is. So the reality is the parallel debuggers are great and they work well. Good news is you probably have access, you definitely have access to them because things like XSEDE exist to give you access to those. Lots of people do pay the licenses and own the licenses. So lots of research institutions have licenses. And again, XSEDE exists so that you have access to tools like this. But there's just no comparable open source versions. They're very, very easy to use. You just compile your code with -G like you do with generic serial debuggers, and everything's in there. It's nice in that these days, because they're very graphical, the interfaces, I'll show you in a second, because the interfaces are graphical, it's important that you have some way of displaying them remotely, when you're running on some 20,000 nodes of a machine. And in the past, the typical way of doing that is X windows, and they do have X windows interfaces, but for various reasons that I don't completely understand. X Windows has gone completely down the gutter the past 20 years in terms of performance. X Windows applications are just incredibly laggy remotely. It's a shame because they used to be faster. For some reason, 20 years ago, an X Windows editor was snappy. Now with hundreds of times faster bandwidth and everything, X Windows applications are all terrible, laggy trash. And so there's an X Windows interface to this, but because of that, DDT, it's owned by ARM now, by the way. So ARM is ultimately the people that control DDT. ARM and DDT have made available a client. It is free. You can download and put it on your laptop, either X Windows or Windows or Mac. And the client is very snappy and interfaces remotely with the debugger. So this is what the client looks like. So does the X window, only the X window is very laggy. And this looks like, for any of you that are used to debuggers and IDEs, this doesn't look that foreign at first. This is a nice debugger. You can set breakpoints, and so you can stop anywhere you want in the source code. If we're doing the Laplace code, which is here in front of us, and your code crashes, you can see what line it crashed on. You can go and look at the values of variables and go, oh yeah, I sent 1,000 of something and I should have sent 1. And anyway, it makes it very easy to figure out what's going on with crashes, and also to stop while the code's running and it's still behaving. You can single step through it. Those are all things you get out of a normal debugger, and they're powerful. I think people underutilize debuggers in a regular basis every day anyway. I mean, even when I'm doing Python coding, I'm still sitting there and, in Spider using my debugger to single step through the code, because that's the easiest way for me to track down stuff even in an interpreted language. So I hope you use debuggers all the time. The parallel debugger, though, brings along the magic up here of being able to select the PE that we're on. Because we know as MPI programmers, when we're staring at the screen, our code isn't on this line. We have 4 PEs. They could be on 4 different lines. And so we can switch between them and see that. We can see which line each PE is really on in our source code. And we can set breakpoints on the PEs and see the values of variables on each one of the PEs. And that's very different from a non-parallel compiler. So here's a breakpoint that we've set in the code. I generated earlier that visualization of the temperature grid. And I said, okay, let's see what the temperature looks like at 3,200 time steps. So I said here, I set a conditional breakpoint. It's kind of nifty. The breakpoints can even be fancy. I said, when the time steps equal to 3,200, stop here, stop the code on this line, 3,200 time steps, and then I can draw a picture. And this up here, let me switch between the different PEs. This variables, for example, we have different variables on each PE. And I can switch between the versions of it, and especially so anyway, for the Laplace code, this is what I could do right here. I could stop it there, and then I could pull up the temperature array. The temperature array doesn't exist as a 1,000 by 1,000 array, but a parallel debugger is so smart at working in a parallel environment, it recognizes maybe it should take that array and string together all 4 pieces of it. It put the array back together for me and let me visualize it, and I can manipulate this and drag it around in real time while the code's paused. So I can put basically all 4 PEs back together in the correct order to visualize the array. That's something only a parallel debugger could even think about doing. So it's great at that. More importantly, at very large scale, you might say that's great, but what about when I run at 10,000 PEs? Do I get 10,000 buttons up here? And the answer is of course not. At very large scale, it has ways of collecting the PEs into groups, and you can find out when anomalies. A lot of times what you're after is, well, PE is something's weird, running on, only happens on a 10,000 PE run. Well, I can go and say which one of these variables isn't the same as the other. So you can find anomalies and go across PEs. It's built to deal with that circumstance. You can connect the running jobs. It also works great with OpenMP and OpenACC and CUDA code as well. It does memory debugging and MPI tracing, which is a nifty thing. This is what MPI tracing looks like when you want to see the patterns your messages are. Now, the good thing here is this is actually public domain stuff we switched into here with the profiler Tau, which also does message tracing. We'll talk about that in a second. But let me see if we got any questions here. Let's see. We got a lot of questions. I want to catch up with them. Let's see. Any recommendations for future advanced programming summer schools? The closest is our international summer school is kind of an advanced thing. It's got it's a little bit qualified from different organizations for all over the world to have their different qualifications. If you happen to be in the United States, XSEDE selects generally from a pool of grads and postdocs. So it's not an answer for everybody, but that's the only kind of advanced parallel programming school out there. How do debuggers work? Well, debuggers work basically by taking in your code and sticking in your code enough information that they can stop at any point in time and tell which variables correspond to what, how things are set, where the state of your code. So yeah, it's taking me 2 or 3 minutes to explain it, which we don't have right now. But basically, it goes and sticks in some stuff in your code to help it so that the code's running. It can stop and look at things and understand what variables correspond to what values in memory. And then it's a matter of just explaining it nicely to you. Eclipse, free scalable parallel debugger. Yeah, I'll be nice and say I wouldn't recommend that, but feel free to take a look and give it a shot. So not hard to try it out with Laplace code, for example. Let's see. Intel One API, NVIDIA. So Intel One API is their term for their collection of, we just talked about that, of DPC and all that stuff. Along with it, they might include we'll talk about, I'll show you VTune and whatnot, some Intel debugger things, but they're also licensed and they're not very good at being parallel. NVIDIA Insight is, so actually maybe you're referring to a question I don't know that's being asked about. Insight, so wherever was that? Okay. Insight is the NVIDIA, that we actually we used Insight earlier with OpenACC to do the profiling of our OpenACC code. Let's see. Using IntelliJ Clang, free and provides good debugging for OpenMP. Yeah, I'm talking, when I say parallel debugger, I'm talking about MPI. I'm talking about massive parallelability. For OpenMP and OpenACC, yes, you have an Insight. You have Intel VTune is probably the best for OpenMP. I talk about those. I'll talk about them in a couple slides. Maybe I do. Maybe I think I do. Intel VTune's probably the best for OpenMP. Insight's what we used earlier with OpenACC. When I talk about parallel debugger, I'm talking about MPI level. I'm talking about massively parallel. So yes, on a single workstation, there are a bunch of parallelish debuggers, but none of them work with at scale. And so yes, IntelliJ Clang, yes, it's not. It doesn't work with MPI at scale. I mean, Power 9 work better in OpenMP or MPI framework. Both. Power 9s are popular chips in some of the world's biggest machines. I think there's a couple in the top 10 list. At least they may be falling out of the list slowly, but they certainly have a presence in the top 500 list. And those machines use both OpenMP and MPI at the same time, just like we're using here. So work well. The nice thing about IDEs and frameworks is if they're any good, they're easy to use and they're easy to test. So I test things out all the time. So you don't have to take my word for it that there's nothing worth using for MPI besides these two. Certainly go and try some of these things out. And I have tried them out. They are not good. But try them. They shouldn't take, especially if you're going to work on code, it's silly not to take and try. If somebody suggests something and says, hey, here's an IDE. Hey, if it's a decent IDE, it takes 20 minutes to install and try, and it should be intuitive. Give it a shot and see if it works for you. So you don't have to take my word for it, but when you're done, I think you'll probably arrive at the same conclusion. And again, I'm talking about MPI debugging here. I am not talking about single node debugging. Single node debugging, Visual Studio's got a fantastic single node debugger in it. I love it. I also have VTune, and I have it integrated with Visual Studio. Sometimes I have it just in a Linux environment separately on bridges. VTune's a fantastic single node debugger for OpenMP stuff. But when we're talking about MPI here, that's when I'm saying there's only two alternatives. So for MPI, really, it's DDT or TotalView. But at any rate, there's better news on the profiling front, again, at large scale with MPI on the profiling front, and that the large scale profilers, there are, on the single node front, there's 1 million profilers. On the large scale profiling side, there is Tau, which is fantastic and works very well and can give us our message passing patterns. So here's that. And you can see, for example, here's nearest neighbor communication in 3D. So if we did the 3D Laplace code, this is a nice way of visualizing the way messages will be passed. Here's how time is being spent passing messages in a particular code I was profiling here. And you can see it broke it down to different MPI routines and what they're doing. And you can see a certain type of communication pattern here happens every 16 PEs, blah, blah, blah. So anyways, a lot of insight that you can gain. Tau is fantastic and is free. When I was talking about node level profilers and debuggers, you have things like VTune, Advisor, Trace Analyzer. You got lots of options at the node level. So at the node level, you got plenty of stuff out there, free and not free and licensed, but also easy to get your hands on or academic licenses. So there's a lot of options. You can investigate and play around with stuff, and a lot of them are decent quality too. So there's no lack of those. Okay, last thing that ties a lot of what we've been doing together is hybrid programming. And if you're worried that we don't have enough time to cover it here, fear not, because we already have covered most of it. The neat thing about the tools that you've learned this week is that they all just fit together like a hand in glove naturally when you go to use them together. And I never get to approach the topic like this because when we teach the MPI workshop by itself, I don't assume anybody knows what I'm talking about with OpenACC. Well, if we talk about OpenACC, nobody knows what MPI is. Here is where I get to talk about combining the two together. And so here is combining OpenACC and OpenMP for the Laplace code. Now you might take me at my word and say, okay, I said you can just combine them together, mash them together, and things work. Well, that's kind of true, because here's what I'm trying to do. I'm going to do it here, but it's not unreservedly true. You can't just literally mash two codes together and they're going to work, because there are some things you need to think about. But if you're an OpenACC or an MPI programmer, they make perfect sense. So here's where I just took and mashed together my MPI solution. So don't memorize this if you don't want to cheat. But this is my MPI solution, and I mashed it together with my OpenACC solution. I just took and combined the MPI directives and the OpenACC directives. And you know what? This runs on multiple nodes and it runs really fast. So this took our run down to the fraction of a second. These timings are a little bit obsolete. So this ran at a nice accelerated pace. It's pretty good, but it's wrong. It's fast and it's wrong. And why is this wrong? And the reason it's wrong is that we do our message passing here. And the message passing is MPI routines. They run, of course, on the host. They're not inside of a kernel, so they're running here on the host. Our message passing is done not from a GPU, but from the CPU. When we're busy passing our messages around right here, where is our actual temperature array and our temperature last array? The answer is it's on the GPU, because if you remember up here, we put a copy command in here to keep it on the GPU. For our OpenACC solution, we want the stuff to stay on the GPU during the entire run. That's our whole point of putting these data regions up here. And it's great. It's on the GPU. And when it gets down to the kernels, it's already waiting for it on the GPU. It's not moving anything back and forth. So this data is all on the GPU. And meanwhile, my MPI code is down here sending it back and forth from the temperature array, which is on the CPU, the host. So I'm sending a bunch of zeros back and forth here while the GPUs are computing way up above. And so guess what? Things do not work right. Now, I can go ahead and fix that problem by just saying, hey, before I send the data, I want to update the host here to pull it back onto the CPU and exchange the data with MPI. And then after the data's exchanged, I want to send it back to the device so the GPU has the right thing to calculate. So here I have fixed the problem of having the data live on the GPU while I'm trying to use MPI to send it back and forth. I fixed it. I do the calculation on the GPU. I bring it back to the host. I send the ghost zones around on the host, and then I send it back to the GPU. And you know what? This runs, and it runs great, because now I've fixed the fact that my data was living in the wrong place, but this is very slow. And so again, with the timings I took when I did this, it's a lot slower. So what can I do to fix the fact? I mean, I need this. I need the data to be, I need the GPU data to be back to send it. Well, what I can do to fix this is recognize I don't need the whole temperature array. I only need the edges, the ghost zones from the temperature array. So I don't need, my message passing is all just the ghost zones, these rows or columns of the temperature array and temperature last array. So I don't need to update the whole thing. I only need to update that strip. So, and you remember we used the array slicing before when we said for printing stuff out, we only want to update a little piece of it. That was nice there. It bought us a fraction of a second. Here, it's a critical. Here now, we are doing exactly what we want to do. Where the data is almost all living on the GPU. We're computing it there. It's running fast. When it's time to send data with our neighbors, we want to get back the ghost zone strip onto the host. We send it with MPI. Then we stick it back on the GPU after it's sent. So it's on our local GPU, and then we compute again. Now we've got something which is fast, uses GPUs, is scalable. This is a fantastic solution that is kind of like just mashing them together, but we need to be actual programmers to be aware of what we're doing, and we have a little tweak, and now we've got something which is very much faster than the original. It's very scalable, and this will scale up hundreds, thousands of times. It's very scalable, and wasn't hard to do. The pieces just fit together and work together like we hope they might. There's nothing here that I technically needed to explain to you. Just from what you know about OpenACC already and what you know about MPI already, you could look at this and go, I get what's going on here. This is making this stuff run on a GPU. Oh yeah, we need the data back on the CPU before we move it around with MPI. Yeah, I better get it back to get the ghost zones back on a GPU before it tries to calculate the next time step. So there's nothing you need to know to make OpenMP and MPI and OpenACC work together. So we're not using OpenMP here yet, but I'll point out OpenMP in the next slide. Let's see if we have any questions here. Okay. How do we compile this code? MPI-CC with the -ACC flag. It's that simple. It is that simple. That's how we compile this code. Now here's some OpenMP combined with MPI. And this example is just some goofy thing I combined just to show you the lowest level kind of stuff. I wanted every thread to be sending messages to every other thread. And typically you wouldn't be doing that. Typically maybe only one thread on the whole node is sending messages or whatever would make more sense. But here's if you want to go lowest level, we can have every single thread send messages to every other single thread. And so that's what this code does. So PE0 thread 0 is sending some data around. They're all sending data around. And all I did was I said, okay, I've got some MPI nodes running. And on each one of those nodes, I want to have threads that are each one sending messages. They get their thread number, and then they send a message to other threads on other PEs. So it's just regular MPI code and regular OpenMP code here. I didn't use directives here. I used some of the API calls instead to make life a little easier. It's probably what you'd do if you were trying to do something like this. But this is our regular MPI stuff and our regular OpenMP stuff. The one difference here is that you do need to tell MPI when you start it up if you're using multiple threads for each one of your ranks. But that's very easy. It's just one of the notes in the MPI thing. If you want to use multiple threads for a single PE, when you call MPI init, you say, hey, I want to allow multiple threads to run on each PE. And it'll do the right things behind the background. But this is just a bunch of threads sending a bunch of messages to each other. So you can do whatever you want. It's that simple. And you can mix and match these things. So when it is compilation time, it said you can, we can have, here's an MPI code with some OpenMP and some OpenACC instructions in it. You do whatever you want. It's very straightforward. Now on bridges, I don't like to waste time, like I said, on local platform stuff. But on bridges, our interact command allows you to mix and match things. So you can ask for different numbers of nodes, different numbers of PEs, ask for GPUs. So you can mix and match things as you want. Intel makes things a little bit more painful than they have to with their defaults. So if you're using Intel compilers, make sure you do this, export this MPI pin thing, or else you just don't actually get multiple cores with OpenMP codes. The details are here. So Intel goes out of their way to be a pain in the butt with some of the stuff. Like the Intel compilers are actually called MPI-ICC, two I's, just because they like to call their compiler, ICC, Intel compiler. So they have two I's, MPI-ICC. Causes countless tickets for us here when people don't use the right wrapper and it ends up using GNU compiler. Anyway, Intel's always got their special way of doing things, but be aware of it if you're using Intel compiler. Intel compilers are good compilers, don't get me wrong, but it's just their refusal to make some standard, to make life easy is annoying, because that stuff's gone on for years. Okay, so each one of these things has its own space now. You know how OpenACC works. You know how, so I guess I lied before. I said it's the last time we're going to see this slide. So you know how these pieces work, and they have their own responsibility in places. So when you start combining them together, right, the pieces just fit. I don't have to go and explain some whole new thing about the rules. When you use MPI with OpenMP, you have to, there's nothing to do. There's nothing to do. You use OpenMP with MPI, the pieces just fit. There's nothing for me to tell you. So you can look at more example codes and find them if you want to, see how this stuff works. But there's nothing more to it. There's nothing here I technically needed to tell you, for you to figure this out or arrive at the solution yourself eventually. This is just the stuff we already learned this week. And that's indeed how all these hybrid codes work. The pieces just fit together. Okay, let me see. If everything is on GPU, why do we need to decompose the domain? Well, because we want to decompose the domain to have multiple GPUs. So our OpenACC code didn't have a decomposed domain, but now we say we don't want to run on one GPU. We want to run on 5,000 GPUs. So if I want to run on 5,000 GPUs, then I need to split up the temperature array into 5,000 pieces, and each piece gets its own GPU. So I have to decompose the domain because I'm using a bunch of GPUs, not one GPU. Each one of these OpenACC kernels is running on one of the GPUs and one of the slices of the temperature array, not the entire temperature array. Yes, we can combine these. Let's see. Each PE uses one GPU. Yeah, the way this is set up by default, yeah, each PE is one GPU. What was the advantage of using MPI and Laplace example with OpenACC? Well, what I was just saying here is now we can make this scalable. Our OpenACC could only use one node, maybe multiple GPUs in one node, but one node. Now we can use as many nodes as we can get our hands on. MPI in the middle. And the ACC MPI example seems back. Why would the MPI in the middle? In the middle. I mean, the MPI here is where it has to be to communicate the computed value. But I don't want to spoil the Laplace code for people. Go look at the Laplace solution. If you're confused about the MPI stuff, understand it first. And there's a Laplace solution. It's just the MPI stuff for you if you're throwing in the towel on the exercises. Like I said, there's a little bit ahead of it. I don't want to spoil the exercise for people. So if you're still working on the MPI exercise, I don't want this to spoil it for you. But there's a solution there. So for the MPI solution, it's the MPI stuff's in the order it's in for a reason. But I don't want to spoil it for everybody. The flag add MPI MPI run. No, MPI, when you grab that stuff, so to MPI run, no, we'll just grab the same nodes it normal does. If they have GPUs attached to them, they'll work. The ACC flag is not. Okay, let's see. We answer each other's questions here. Would MPI perform better on a single node than OpenMP? This is a question we've answered multiple times here today in different contexts and everything. And the answer is, it's not surprising if it does because of cache management stuff. So I don't want to go over the entire discussion again, but yes, it's not surprising that OpenMP on a single node would perform somewhat better. We're only talking a couple % here and there than OpenMP. OpenMP can only be on one node. Yes, that is the case. And for multiple nodes, we need hybrid OpenMP and MPI. Yes, that is the case. Okay. Okay, with that, we are caught up on questions, and I'm happy to answer them until time runs out very shortly. But while I'm doing that, I want to make sure I do throw up our official goodbye slides with information that you should be aware of. First of all, there's surveys on this, and we really take your feedback seriously. The written comments in particular, I guarantee you, I personally read every single written comment because there's written comment section. I think that's where we get the most insight, when people really can tell us their thoughts. There's a number of things on there too, but we take it all very seriously. If this was helpful to you, it's because earlier people helped us to shape this event. So please do answer that. You have weeks remaining on this, and after which you can easily request an allocation, a startup allocation on any of the XSEDE platforms very easily. We have our own, this link is, I think, not as concise as it could be. So we've written an easier to understand instructions link because it shouldn't take you more than 20 minutes to apply for this time. But this link goes in a few circles. But anyway, they'll both get you there. It's just if you find yourself spending more than 20 minutes on the application, you're doing it wrong. It's very easy to apply for time. So with that, let me give the official goodbye, although we have another 5 minutes or so to hang out and answer questions. Thank you all for your time and attention. I hope these skills you've learned turn out to be useful to you. If they do help you in a project, I am always delighted when I hear back from people and they tell me, hey, this really helped me in my career, with my project or whatever. It's my intent that most of what you learned here, you can go back and apply immediately to a project that you're doing right now. This is real skills, hands-on skills, not just a bunch of buzzwords. So I hope it helps, and I hope that you can let me know if it's been helpful to you. I run into people all the time and they get to thank me in person, but I'm always delighted if I get an email from somebody and let me know. Much thanks to Tom and Steve for all the effort that they put in the background. As you can see, keeping up with the fire hose, it's been our chat channel and whatnot all week. And for Steve for keeping everything online and running it. I think things have gone pretty smoothly. So I see a fire hose of thank yous here, and you're all very, very welcome. If there are any questions hidden in there that are streaming off the top, maybe we'll take a pause, get any questions in here. But let's see. But anyway, your feedback there, like somebody saying this course should be split into intro, intermediate, and advanced. I'm not sure how that could be done, but please let me know about how you think we could divide things. I mean, that's the kind of feedback I'm delighted to hear. Please give me it in a less concise format in the feedback thing. What is the criteria to get expert guidance on stuff? XSEDE has what they call ECCSS, which is guidance people to give you consulting on projects and whatnot, where you can ask for people to help you with the project. And they're happy to do that. That's one of the things you could apply for at XSEDE. So feel free to do that. Somebody saying you already got results with OpenMP. Congratulations. Thank you. That's gratifying to hear. I'm glad to hear you were able to do that. That's the ultimate hope we have. Somebody asking, is it worth parallelizing a particular example here? We don't have time to go into details, but if you spend your time waiting for your results and it's getting in the way of your progress in your research, you now have the tools to parallelize things and speed them up. So I'd say if you're sitting around waiting for that Python script or MATLAB job if it's costing you progress, you have the capability now of parallelizing it. Parallelizing MATLAB code. MATLAB has a lot of effort invested in their parallel toolkit to help you parallelize stuff. I mean, there's actually MATLAB MPI stuff, but you might want to take a look at the parallel toolkit. And somebody even posted a link here for some GPU coding stuff. So MATLAB has invested over the past decade plus an awful lot in helping to parallelize things that they do, hopefully as automatically as possible. That's where the parallel toolkit comes in. Okay, I think we got about 60 seconds before we are off the air here. So once again, everybody, you're very welcome. I'm glad it was worthwhile for everybody. And suggestions for future topics like finance track or whatever, please put those in writing in the evaluations and the feedback. That's my ammunition when I go saying what can we get resources to do in the future. Having your evaluations and your suggestions are what give me that ammunition. Well, with that, I think we will let Steve and Tom get on to their well-deserved weekend.